Far beyond the warm glow of our sun, where light fades and silence deepens into something almost eternal, a tiny machine continues to move onward. It is Voyager, the little messenger built by human hands decades ago, now drifting in a place where no voice or radio from Earth sounds clear. This fragile craft, smaller than a school bus and lighter than a family car, carries with it the whispers of our world, a faint signal, a golden record, and a promise that we once looked up and wondered. It spins gently, antennas pointed back home, its body coated with dust older than memory, but it still listens, still speaks, still survives. In the emptiness that surrounds it, Voyager feels no warmth, no pull of comfort from the sun. What it knows instead is the steady hum of distant radiation and the slow rhythm of cosmic rays tapping at its instruments. The power that once burned bright inside it now flickers softly, a fading candle struggling against the cold. Yet it endures, because endurance is what it was built for. It has passed the borders of our solar system, not a wall but a vast and delicate threshold, where the wind of our sun finally bows to the greater winds of the galaxy beyond. This region, the edge of the heliosphere, is not a solid frontier but a shimmering skin where two cosmic oceans meet. On one side, solar particles drift outward like a long sigh from the sun. On the other, the interstellar medium presses inward, ancient and cold. Voyager floats between them, like a leaf resting between tides, measuring invisible tremors of pressure, magnetism, and soundless storms. Each signal it sends back is faint, a thread of light crossing billions of kilometers, yet when it arrives, it speaks volumes about the shape of our cosmic home. For scientists on Earth, every bit of data is a fragment of a dream. They gather around the signals as if listening to a whisper through wind, piecing together patterns, pulses, and frequencies that reveal how our sun breathes and how space itself hums. Voyager tells them about the density of plasma beyond the heliosphere, about magnetic fields twisting through voids, and about a boundary that is not an end but a beginning. Each discovery adds another verse to the story of exploration, a story told not with footsteps, but with radio waves traveling through night. When it was launched in 1977, no one could have imagined it would still be alive this far into time. Its original mission was only meant to visit Jupiter and Saturn, to photograph their moons, measure their fields, and wave goodbye. But the universe had other plans. The trajectory it followed, slingshot by gravity's gentle pull, sent it on a path that would carry it forever outward. Now, all these years later, its cameras long asleep and its instruments fewer, it continues to serve, not by seeing, but by feeling. It feels the texture of cosmic winds, the murmur of charged particles, and the echo of creation itself. There's something deeply human about this persistence. Voyager is, in a way, our reflection cast into the stars. We, too, are small, fragile, driven by curiosity more than necessity. We build, we dream, and we send our creations into the unknown hoping they will outlive us, to tell someone, somewhere, that we existed. And Voyager does that. In the cold, it continues to hum a song that began in Earth's warmth, a melody of mathematics and wonder. Even if no one hears it in the distant future, it will still be there, playing on, silent but eternal. The messages engraved upon its golden record carry a greeting from every corner of Earth, the sounds of rain, the laughter of children, the chirping of birds, and greetings in dozens of languages. These are not mere recordings, they are offerings, pieces of our spirit sealed in metal. Voyager carries them like a pilgrim bearing sacred relics across the dark. If one day, some other intelligence finds it, they will learn not of our wars or fears, but of our hope that we looked beyond and wished to connect. As it drifts farther, the sun becomes a tiny star behind it, no brighter than any other in the night sky. The solar wind fades, replaced by interstellar particles that move differently, slower, heavier. Voyager senses the shift. Its instruments register faint signals of plasma density, marking the transition, the place where the sun's influence ends. It's not a dramatic boundary, but a subtle change, like the quiet between waves on a shore. For Voyager, it is both an ending and a beginning, the crossing from the known to the unending. This edge of the heliosphere has long fascinated scientists. It's the place where our solar system breathes out and the galaxy breathes in. The two meet and mingle, sometimes clashing, sometimes merging softly. The temperature rises here, unexpectedly, a mysterious layer of heated plasma surrounding the sun's domain, glowing at tens of thousands of degrees, invisible yet powerful. Voyager's instruments caught its presence, a discovery no one predicted. It is as if the sun's last breath leaves behind a warm mist before dissolving into the cosmic sea. Voyager's sensors record the hum of plasma waves moving through this hot boundary. Each wave tells a story of charged particles colliding, of energy exchanged, of space vibrating in a rhythm no human ear can hear. Scientists translate these vibrations into sound, a ghostly chorus that resembles music from another world. Through it, we can almost imagine what it feels like to float there, the slow undulations, the faint tremor of distant storms, and the endless stillness in between. Voyager becomes our ear, our quiet witness to the song of space. Even now, as it grows older, its power is fading. One by one, its instruments are turned off to save energy. Its radioisotope generator, once full of heat, now cools with every passing year. Yet it continues to send its reports, refusing to fall silent. This resilience is astonishing, almost poetic. The little craft was never built to endure forever, but it has defied the expectations of engineers and dreamers alike. Like a lantern floating down a cosmic river, it drifts on, light dimming but purpose undiminished. The scientists who still listen to Voyager speak of it with affection, as if it were a living thing, a colleague, a friend, a stubborn survivor. They know one day its voice will stop. The signal will fade into static, and silence will return. But that moment will not be an end. It will be the continuation of its journey, unmonitored but not forgotten. Somewhere out there, in the vastness between stars, it will keep going, carrying the message that once, on a small blue world, a species dared to reach out. Voyager's golden record is not only a greeting, it is also a time capsule of our moment in history. The sounds of Earth it holds are now decades old, echoes of a time when we first began to understand our place in the cosmos. The laughter, the music, the heartbeat, all captured before many who live today were even born. It is, in a sense, a fossil of emotion, traveling through the void faster than any human body ever could. If found, it could tell future minds about a species that longed for contact, even when alone. What Voyager leaves behind is more than data, it's a shift in perspective. It reminds us that boundaries are illusions. The universe doesn't draw lines, we do. The edge of the heliosphere, the end of the sun's breath, the start of interstellar space, all of these are parts of a continuous ocean. Voyager's crossing is our awakening, proof that we are part of something larger, something unending. Its distance teaches humility, its persistence, hope. At times, scientists send commands, but the delay is immense, over 20 hours for a single signal to travel each way. It's a conversation through time, not distance. Each word they send takes patience, like speaking to someone who lives across light years. When Voyager replies, its voice is faint but steady, a pulse that says, "I'm still here." And that heartbeat, though faint, has inspired generations. It is a reminder that even the smallest signal can bridge the deepest silence. In the silence between transmissions, one can imagine Voyager drifting through fields of dust illuminated by distant stars. The light that touches it may have traveled from suns long dead. Perhaps it passes fragments of frozen comets or ancient atoms once part of other worlds. Everything around it is history billions of years old, and Voyager becomes part of that history now, a moving relic, carrying new stories through ancient space. No other human creation has ever traveled this far. It is the most distant ambassador of Earth, farther than any probe, any dream, any reach of our radio waves. Its journey redefines what it means to explore. Not every exploration requires a destination. Sometimes, to simply move outward is enough. Voyager does that, endlessly. It journeys not to arrive but to remind us that exploration is a way of being, not a place to end. Perhaps one day, in some unimaginable future, Voyager will drift close to another star system. Its golden record will still glimmer faintly, untouched by time. Maybe it will pass unseen, or maybe some curious beings will find it, study it, and hear our message. They may learn about our oceans, our greetings, our wish for peace. And through that discovery, they might understand that once, long ago, we, too, looked up at the same stars and wondered if anyone was there. Until that day, Voyager moves on. The sun grows dim behind it, and ahead lies eternity, the interstellar night, unbroken and vast. It will cross regions of darkness no human can imagine, where even light bends differently, where silence is older than time itself. Yet within that silence, Voyager carries something loud and eternal: curiosity. That is the true power it holds, not the data it sends, but the spark it represents. Each time we think of Voyager, we remember that the universe is not empty. It listens, it echoes, and it holds our stories. The little messenger at the edge continues to write one, slowly, across the backdrop of infinity. Its path is endless, its purpose simple: to keep going, to keep whispering back to us across the dark. And as long as its faint signal still reaches home, we will listen. Because in its quiet endurance, we hear not just a machine, but the heartbeat of our own longing to know what lies beyond. At the farthest edges of our sun's influence lies a boundary that isn't really a wall, but a whispering veil, the Heliopause. It's where the solar wind, that constant flow of charged particles streaming outward from the sun, finally meets its match. For billions of kilometers, this wind carries the warmth and touch of our star, shaping an invisible bubble that cradles every planet and moon we know. But here, at this distant threshold, the sun's breath weakens, slows, and yields to the greater breath of the galaxy itself. Voyager floats here, feeling the last faint tremor of home. The Heliopause is a place of balance and collision. On one side flows the solar wind, energetic, hot, and filled with the heartbeat of the sun's activity. On the other side lies the interstellar medium, colder, denser, ancient. These two rivers of particles meet, swirl, and press against each other, forming a dynamic and shimmering boundary. It isn't fixed, it moves and shivers with the sun's moods, expanding when the solar wind grows strong, retreating when the sun's pulse quiets. Voyager's tiny instruments measure these changes like fingers feeling the edges of an invisible tide. When Voyager first approached this mysterious border, no one knew exactly what it would find. Theories painted different pictures: a sharp edge, a gradual fade, perhaps even a chaotic mix of energies. What the spacecraft revealed was subtler, more elegant. The transition was not abrupt, but gentle. The density of particles shifted, magnetic fields turned, and the hum of plasma waves began to sing in a higher key. It was as though Voyager had stepped from one ocean into another, the temperature of the water changing slowly around it. This boundary, though unseen, is immense beyond comprehension. The heliosphere, the bubble created by the sun's wind, stretches roughly 120 astronomical units from the sun, over 18 billion kilometers. Everything within it, from Mercury to Neptune and the scattered comets beyond, floats inside the sun's invisible atmosphere. The Heliopause marks its edge, the line where the sun's energy no longer dominates. Beyond it, interstellar space begins, a vast expanse filled with material left over from ancient stars that lived and died long before ours was born. When Voyager crossed this edge in 2012, humanity, for the first time, touched the true outside. Its instruments detected a sudden increase in cosmic rays, particles arriving from the galaxy beyond, and a sharp decrease in those flowing outward from the Sun. That change told the story clearly. The little probe had left the cradle of the solar wind. It was no longer inside the Sun's domain. It was sailing in the Milky Way's open waters. This was the moment when our species, through a small metal craft, truly became interstellar. The region around the Heliopause is not calm, though. It ripples with invisible turbulence. Solar storms, born from flares and coronal mass ejections, travel outward for months or even years before they reach this edge. When they do, they crash into the interstellar medium like waves meeting a cliff, sending shocks and waves echoing through plasma. Voyager feels these as tiny bursts of vibration, the space around it briefly trembling before settling once again into stillness. Each tremor carries news from home, the Sun's distant heartbeat, still felt across the void. The interstellar medium pressing against the heliosphere is ancient and rich with history. It is made of gas and dust expelled by long-dead stars, carbon, oxygen, iron, and other elements scattered through time. When these particles meet the solar wind, they do not mix easily. They push and twist, forming magnetic boundaries and pockets of pressure. Voyager's sensors trace these shapes, mapping the texture of the frontier. From its data, scientists imagine the Heliopause not as a perfect sphere, but as a distorted bubble, stretched by the motion of the solar system as it travels through the galaxy. Inside this bubble, Earth has always been sheltered. The heliosphere deflects many cosmic rays that might otherwise bombard our planet, shaping the radiation environment of the solar system. It is, in a sense, our protective cocoon. The Heliopause, then, is its skin, the thin membrane separating safety from exposure. To understand it is to understand the shield that has allowed life to flourish on Earth. Voyager, drifting silently beyond it, now studies what lies outside that shield, revealing what kind of universe we are truly surrounded by. Scientists describe this region as an interface, a frontier between two vast systems. The Sun's magnetic field, carried outward by the solar wind, meets and tangles with the interstellar magnetic field. These interactions are complex and unpredictable, creating vortices and folds where charged particles spiral and accelerate. Voyager's instruments detect subtle fluctuations in magnetic direction, showing how these fields dance and blend. From this data, researchers craft models of cosmic weather, predicting how our solar system interacts with the galaxy like a small boat in a larger ocean current. The discovery of the Heliopause transformed our understanding of the solar system's limits. For centuries, people imagined the solar system as a collection of planets orbiting in space, perhaps surrounded by emptiness. Now we know it is alive with structure, shaped by forces we cannot see. The heliosphere breathes, moves, and reacts to its environment. The boundary Voyager crossed is not static, it changes with the Sun's 11-year cycle, growing and shrinking, shifting its shape. The edge where the Sun's breath ends is, in truth, always in motion. To cross such a boundary is to experience a kind of rebirth. Voyager entered interstellar space not by crashing through a wall, but by slowly drifting out of the Sun's influence, like a child walking from the light of home into the cool, endless air of a valley beyond. The radio waves it sends back travel through this new medium differently, slightly distorted by the interstellar plasma. Scientists listen to these distortions, decoding them into insights about temperature, density, and pressure. Even now, Voyager teaches us how to hear the voice of the galaxy itself. The Heliopause also carries a kind of poetry. It marks the end of the Sun's dominion, the point where our star's warmth fades into insignificance. Yet, rather than being a place of loss, it is a place of connection. Beyond it lies the interstellar medium, which is, in many ways, the birthplace of stars. The same material pressing against the heliosphere today will, in time, collapse elsewhere to ignite new suns, new worlds, perhaps new life. Voyager's journey, then, is not just outward, but into the future, into the cycle of creation that binds all things. At this edge, temperature and density behave strangely. Voyager recorded plasma that was unexpectedly warm, tens of thousands of degrees hotter than models predicted. Scientists were puzzled. Theories began to form suggesting that magnetic reconnect ion, the breaking and merging of magnetic field lines, might be heating the plasma. It's a subtle, invisible fire that flickers between stars, unseen but real. In this thin, hot sheath, the sun's breath mingles with the galaxies, creating a cosmic glow without light. It is here that the sun's influence fades not in silence, but in warmth. This warmth, this faint echo of energy, is the sun's goodbye, its last touch reaching into interstellar space. Voyager, as it passed through, recorded the song of this farewell in radio frequencies. Scientists converted these plasma oscillations into sound, revealing a gentle hum, a long, soft tone that rises and falls. Listening to it is like hearing the edge of a dream. It is the sun's last sigh, fading but never quite gone, a reminder that even at the edge of emptiness, energy still whispers through space. The Heliopause teaches us about boundaries that exist but do not confine. It reminds us that endings are often beginnings in disguise. The sun's breath ends here, but what lies beyond is not emptiness, it is continuation. Voyager's crossing proves that the universe is seamless, that the forces flowing from stars are not confined to them but merge with the greater whole. The boundary is simply where one rhythm fades and another begins. The melody does not stop, it changes key. Each day that Voyager moves deeper into interstellar space, it continues to test the thickness of the boundary behind it. The instruments still measure how far the sun's influence stretches, how strong the magnetic field remains, how dense the plasma grows. What scientists learn helps them predict how other stars carve their own bubbles, how their winds shape nearby space. The heliopause around our sun is just one of countless such boundaries across the galaxy, each a soft shell cradling worlds within. And so, this little spacecraft becomes our cosmic scout. It moves where no sunlight falls, guided only by momentum and memory. Its golden record remains sealed, carrying messages from a world far inside the heliosphere. Now, beyond that edge, it drifts through the galaxy's ancient breath, wrapped in silence. Every pulse of data it sends is an echo from the frontier, a postcard from the place where the sun's story ends and another begins. The heliopause may sound distant and scientific, but it is also profoundly human. It shows us the scale of our curiosity, how far we are willing to reach just to understand where we live. Voyager's presence there is a quiet declaration that even in the darkest, coldest parts of space, human thought endures. We cannot yet go there ourselves, but our machines can. And through them, we have touched the border between solar and stellar, between familiar and infinite. As Voyager moves farther, the heliopause remains behind it, a fading threshold in the cosmic night. The data it collected will continue to teach for decades, helping us refine our sense of how the sun interacts with the galaxy. Each new insight reminds us that we are not separate from the cosmos, but part of its breathing, pulsing life. The heliosphere is our womb, the heliopause its skin, and beyond it lies the open universe waiting for us to wake. The sun's breath will always flow outward, reshaping its bubble, meeting the galaxy's pressure in an endless dance. Voyager's crossing is but one moment in that grand rhythm, a note held across centuries. It tells us that even when energy fades, something remains. Movement continues. The cosmos does not stop, it evolves, expands, breathes. And somewhere within it, a tiny traveler drifts, its antenna still turned toward home, carrying the memory of where the sun's breath once reached. When Voyager drifted through the outer layers of the heliosphere, scientists expected a descent into even colder, quieter regions of space. Instead, the little spacecraft detected something astonishing. The plasma around it, the thin gas of charged particles filling space, was far hotter than anyone predicted. Not a flame in the way we know it, but a vast, invisible furnace of energy, with temperatures soaring to nearly 50,000 degrees. It wasn't a blaze that could be seen or felt, but one that shimmered through numbers and data, a heat born from motion, not from light. This was a puzzle. Out there, sunlight is a ghost, barely brushing the spacecraft with warmth. No atmosphere surrounds Voyager to trap heat, and no stars lie close enough to pour their energy into the plasma. Yet, the instruments registered it, a steady, persistent layer of hot, thin material pressing like a veil between the solar wind and the interstellar medium. Scientists named it the Heliopause thermal wall, though in truth, it was not a wall at all. It was more like the soft edge of a flame, flickering unseen, where energy from two worlds met and merged. This heat comes not from combustion, but from motion and collision. The solar wind races outward from the Sun at hundreds of kilometers per second, carrying magnetic fields and charged particles. As it slows near the heliopause, it meets the resistance of the interstellar medium, slower, denser, and flowing in the opposite direction. The collision doesn't make fire, it makes frictionless shock. Energy is transferred, particles are accelerated, and heat blooms without light. It's a form of invisible turbulence, a cosmic heat born of space itself moving. When Voyager's detectors first sensed this unexpected temperature rise, the discovery was both thrilling and perplexing. For decades, models of the heliosphere suggested the boundary should be cool and diffuse, where pressure simply equalized between the solar wind and interstellar plasma. Yet Voyager's data said otherwise. It had stumbled into a zone where energy collected like mist between two seas. The Sun's expelled particles, instead of dispersing into the void, were trapped and heated, spinning and colliding until they glowed with energy, though no eye could ever see that glow. Scientists began to reimagine what the edge of the Sun's influence looked like. It was no longer just a quiet transition, but a storm zone of microscopic intensity. Magnetic fields tangled, reconnecting, and snapping, each event releasing bursts of energy that rippled outward. The region became a cauldron of electric and magnetic interplay, with currents weaving patterns too complex to visualize. Voyager was not just crossing into interstellar space, it was passing through the Sun's final furnace, where the last of its wind burned itself into stillness. This furnace of particles told astronomers something profound about how stars shape their surroundings. Every star in the galaxy, great or small, breathes out a wind that carves its own bubble in the interstellar medium. Around each of these bubbles lies a region like Voyager's discovery, thin, hot, and alive with invisible fire. The edge of the heliosphere, then, is not unique, but part of a galactic pattern, a cosmic fabric woven from countless boundaries like ours. Voyager's crossing gave us the first touch of that texture, letting us feel what it means to live inside a star's breath. Inside this heated layer, temperature does not behave as it does on Earth. Here, hot does not mean warmth that could burn a hand, it means motion, the speed of atoms and ions zipping through near vacuum. Each one carries immense kinetic energy, moving so fast that, despite their rarity, their collective motion forms a measurable heat. It's a paradox, something nearly empty, yet blazing with invisible activity. Voyager's instruments sensed the density, counted the charges, and revealed a picture of chaos that somehow held balance, a steady, restless equilibrium between the solar and the interstellar. The particles in this zone move like dancers in a silent, endless waltz. They spiral along magnetic field lines, looping and weaving through invisible structures. Occasionally, they collide, exchanging energy and direction. Each collision adds to the heat, stirring the plasma into a gentle turbulence that never ceases. The space around Voyager, though silent, was alive with this motion, a kind of whispering storm too subtle for sound, too vast for sight. The spacecraft was floating in the sun's final breath, where warmth survived only as motion among ghosts. For Voyager's team, the readings raised new questions. If the boundary between the sun and the galaxy was so hot, what sustained it? How could such a thin medium hold so much energy without radiating it away? The answer, they found, lay in the nature of plasma itself. Plasma can trap magnetic energy the way a spring holds tension. When magnetic field lines reconnect, they release bursts of that energy as heat. The heliopause, it seemed, was not static, it was a living boundary, flexing and snapping as fields merged and broke. Voyager's sensors were feeling the tremors of this invisible dance. Over time, more data confirmed this strange warmth was real and consistent. It wasn't an artifact of the instruments or a passing solar event. It was a persistent feature, a shell of heat surrounding the sun's domain. This finding reshaped our understanding of stellar boundaries across the galaxy. If our own heliosphere has such a heated edge, then so might every other star. These layers, overlapping through interstellar space, could influence how radiation travels, how cosmic rays move, and even how the galaxy itself breathes. The heliopause, then, is not a barrier, but a seam in the fabric of the cosmos. Voyager's journey through this heated zone was like passing through a fog of fire. Yet it continued smoothly, untroubled by the forces around it. The plasma, though hot, was incredibly thin, a few particles per cubic centimeter, too diffuse to exert pressure on the craft. It simply drifted through, its instruments open and listening. From this silence came a revelation. The boundary between solar and interstellar is not defined by emptiness, but by energy. Space is not a void, it is alive with movement, humming with electric potential and heat unseen. Scientists compared this unexpected warmth to what they call collisionless shocks, boundaries in plasma where energy converts to heat without direct impact. These shocks occur around supernova remnants, in stellar winds, and even near Earth's magnetic bow shock. Voyager's discovery showed that the same physics governs the largest scales of the universe. Wherever energy meets resistance, heat is born. And in this case, it was the slow, steady resistance of the galaxy pressing against the sun's exhale, a cosmic sigh transformed into warmth. The discovery carried philosophical weight too. It meant that even at the farthest edge of the sun's influence, where we might imagine cold and emptiness, there exists life in motion, not biological, but physical. The particles hum, the fields twist, and the universe stirs. Voyager's sensors, in their quiet precision, captured a truth that resonates beyond science. Nothing in the cosmos is truly still. Even where the light ends, energy continues to dance. The sun's breath does not fade into silence, it transforms into heat, into motion, into something enduring. From this revelation, new mysteries unfolded. If the heliopause glows with invisible warmth, what lies beyond it in the interstellar medium? Does this heat influence how cosmic rays enter our solar system, shaping the radiation that touches Earth? Does it affect how magnetic fields link between stars? Voyager's data hinted that these regions might act as filters, modulating the flow of energy between systems. The heliosphere, it turned out, was not an isolated bubble but part of a vast, interconnected web, the galactic bloodstream through which energy flows endlessly. When scientists transformed the plasma data into sound waves, they heard a strange, resonant hum, the signature of the heated plasma vibrating in space. It was not a roar, but a long, steady tone, rising and falling like a sigh. To listen to it was to hear the voice of the boundary itself, the sun speaking softly to the galaxy. Each vibration represented charged particles trembling with warmth, echoing across billions of kilometers. Voyager had not just found heat, it had found a sound, the faintest music of interstellar transition. To describe this warmth as fire would be misleading, yet it carries the spirit of one. Fire, after all, is transformation energy shifting from one form to another. That is what happens here, on this invisible frontier. The sun's energy, carried outward for billions of miles, finally changes form. Its wind slows, its fields bend, and its power disperses into motion. The heat Voyager measured is that transformation captured mid-breath. It is the sun's farewell kiss, burning softly into the skin of the galaxy. The existence of this layer also hints at protection. The heated plasma acts as a cushion, absorbing shocks from interstellar space before they reach the inner solar system. It softens the impacts of cosmic rays and stabilizes the bubble around us. In a way, this furnace of particles is both shield and signal, a zone where the universe negotiates balance. Voyager, by measuring it, revealed not chaos but harmony, the sun and galaxy coexisting through temperature, motion, and magnetism, each giving and taking in an endless exchange. Even now, long after its instruments first felt this heat, Voyager continues to move deeper into the interstellar medium. The memory of that warm boundary travels with it, encoded in its data and stored in the minds of those who study it. Future explorers, human or robotic, will pass through similar regions around other stars, and they will know to expect not emptiness, but energy. Voyager has shown that the edge of every star's breath glows, unseen but real, a furnace in the cold. This discovery reshaped not only astrophysics but also imagination. The Heliopause was once thought to be a silent void, a curtain closing the sun's influence. Now it is known as a place of vibrant interaction, where particles collide and energy flows. It is both fragile and powerful, vast and delicate, invisible but alive. Through Voyager, we learned that even the coldest regions of space can hold warmth, not in light or fire, but in motion, in the ceaseless heartbeat of the cosmos itself. In the story of Voyager, the discovery of this heat stands as one of its most poetic triumphs. It showed that exploration is not always about finding new worlds or moons, but about uncovering the unseen structures of existence. A tiny probe, powered by fading plutonium and guided by radio whispers, revealed that the universe burns in ways beyond human senses. In the darkness, it found warmth. In the emptiness, it found energy. In silence, it found the voice of the sun's final breath. And so, the little spacecraft continued on, leaving behind the glowing boundary where the sun's wind becomes the galaxy's air. The heat it discovered remains there, circling unseen, part of the ever-shifting frontier of our solar system. Voyager's instruments no longer feel it directly, but the data endures, echoing through laboratories and minds. The furnace of particles is still burning, slowly and endlessly, a reminder that even in the deepest dark, there is always a trace of fire. When scientists first received Voyager's data from beyond the Heliopause, what appeared on their screens didn't just surprise them, it silenced them. The readings, columns of numbers scrolling endlessly, spoke of a region far hotter and denser than anyone had imagined. The plasma temperature was close to 50,000 Kelvin, far above expectations. Yet the density of that same plasma was incredibly low, just a few particles per cubic centimeter. That paradox alone made scientists stop and breathe, realizing they were seeing something no human had ever touched before, the raw mathematics of the sun's last whisper. Numbers are often thought of as cold, but here they burned. They described a place so alien that imagination struggled to follow. Voyager's instruments, operating millions of kilometers from home, had detected changes in frequency and vibration that corresponded to this intense heat. These figures weren't noise, they were the language of the universe itself, translated into electric pulses and data packets. As the analysis deepened, the temperature, pressure and speed of the plasma aligned into a pattern that didn't belong to either solar or interstellar space. It was something between a liminal region written in equations instead of light. Each new data transmission arrived faintly, taking over 20 hours to reach Earth, and yet every byte carried weight. Scientists huddled in quiet rooms, watching graphs rise and fall with delicate precision. The particle counts spiked, then flattened. The frequencies of plasma waves shifted. Magnetic field measurements twisted slightly, showing that Voyager had truly crossed something monumental. The heliosphere's edge, long imagined as a smooth fade, revealed itself through these numbers as a structured and dynamic frontier. To read them was to feel or to understand that nature's complexity unfolds best in silence and patience. The density figures, though tiny in human terms, spoke volumes. A few particles per cubic centimeter may sound like emptiness, but on the cosmic scale, it is matter enough to shape boundaries, to form invisible walls of pressure. Those numbers told scientists how the solar wind, expanding outward, finally met the galaxy's interstellar flow. The balance between them was delicate, so precise that a single extra proton could shift the shape of the heliopause. Voyager had become a cosmic scale, weighing forces larger than imagination and older than time. The speed readings were another revelation. The solar wind slowed drastically as Voyager approached the boundary, dropping from hundreds of kilometers per second to almost nothing. That deceleration, recorded across countless samples, marked the sun's breath coming to rest. Beyond that, the interstellar particles moved differently, slower, more uniform, guided by the galaxy's magnetic field instead of the sun's. The numbers painted a picture of motion fading into stillness, a graceful pause where two immense systems shook hands and exchanged energy. One set of figures in particular, the plasma oscillation frequency, became the key to unlocking the mystery. When solar storms sent shocks outward, they created waves that rippled through the plasma. Voyager's instruments detected these waves, and by measuring their pitch, scientists calculated the density of particles around the spacecraft. From these calculations, the temperature emerged. What they found was astonishing. The plasma beyond the heliopause was not cold and still, but alive, vibrating with warmth and motion. The sun's influence had not vanished, it lingered, softly heating the cosmic sea. Even the magnetic field readings carried subtle poetry. The direction of the magnetic lines barely changed as Voyager crossed the boundary, suggesting that the solar field and the galactic field were aligned more closely than expected. This meant that the sun's influence, though fading, blended smoothly into the galaxies. The numbers were gentle in their message. There was no clash, no sharp break, only continuity. Space itself seemed to prefer cooperation over conflict, choosing harmony between fields rather than chaos. Every new transmission tested the patience of those who waited. It took nearly a day for Voyager's signals to travel from where it was to Earth, and another to interpret them. The data rate was painfully slow, like listening to a whisper through a storm. Yet, every whisper mattered. Each fluctuation, each decimal point, contained the signature of a distant environment. To think that such fragile signals could reveal truths about billions of kilometers of space was humbling. The numbers didn't just inform, they connected. They bridged light-years of silence between machine and mind. When the first comprehensive plots were drawn, showing temperature against density, scientists saw something breathtaking. A smooth curve, a transition where energy seemed to collect instead of disperse. The sun's power did not simply vanish at its edge, it transformed, condensed into heat and motion. These graphs became modern constellations, star maps of invisible forces. To trace them was to navigate the unseen borders of our solar system, to understand that what appears as empty darkness is, in truth, a living gradient of change. And in that realization, the numbers took on emotional depth. They told not just a story of physics, but of persistence. Voyager's instruments, built with 1970s technology, still functioned with astonishing precision. Their readings were proof that even old tools could reveal timeless truths. Every voltage measurement, every calibrated drift, echoed human dedication, people who had dreamed, designed, and dared to send something small into the infinite. The data was not just scientific, it was personal, carrying the fingerprints of generations of dreamers. The numbers describing the plasma's heat revealed another mystery. How could something so thin hold such energy for so long? Theorists proposed that magnetic turbulence was constantly feeding this heat, converting the sun's fading motion into internal agitation. The plasma, in effect, stored memory, the leftover energy of solar winds that had been traveling for years, finally compressed at the heliopause. The figures describing this balance read like a quiet equation of patience: distance times time equals warmth. Even at the farthest edge, time itself had become a furnace. Other readings confirmed the region's dynamic nature. Voyager detected fluctuations in cosmic ray intensity, tiny, rhythmic rises and falls. These hinted that the heliopause breathes, expanding and contracting with the sun's cycles. When solar activity increases, the boundary bulges outward. When it quiets, the edge retreats. The numbers showed this motion as gentle undulations, like the lungs of the solar system filling and emptying. Even from 18 billion kilometers away, the sun's pulse could still be felt. The mathematics of breath extended across the void. The numbers also revealed how long this heated region extends. The boundary wasn't a thin line, but a shell tens of millions of kilometers thick. Voyager's journey through it lasted years, not moments. During that time, every reading helped refine its shape, not spherical, but distorted, sculpted by the galaxy's pressure. The heliosphere, it seemed, is like a windsock, stretched by the movement of our solar system through the Milky Way. The data reflected this asymmetry perfectly, showing how space itself can have direction and flow, even without up or down. As the analysis deepened, small irregularities emerged, subtle spikes and dips that hinted at turbulence and microshocks. These tiny deviations in the numbers told stories of energy release, of magnetic reconnect ions and swirling eddies too fine to imagine visually. They were fingerprints of chaos at the edge of order. Voyager had not only crossed a boundary, it had entered a laboratory of the universe, where physics itself still experiments. Each number was a piece of that grand, unseen experiment's record, preserved in binary form for minds to decode. Sometimes the most haunting data wasn't what changed, but what stayed the same. Despite all that heat, despite the turbulence and transformation, Voyager's signal remained steady. Its frequency wavered slightly with plasma conditions, but its strength endured. This constancy told scientists something poetic: even amid chaos, stability can persist. The spacecraft had found equilibrium in the midst of shifting energy, like a calm boat drifting through stormy waters. The math of balance existed even in the wildest frontiers. To most of the world, these discoveries are lines in a journal, published and cited. But to those who work with the raw numbers, each value holds intimacy. Scientists often describe how they feel when the next data packet arrives, a strange, almost reverent stillness. They see in those readings not just science, but connection. The numbers, after all, are the only voice Voyager has left. Through them, it says, "I am still here." That realization alone makes every decimal point glow with meaning. In one report, the energy distribution curve caught particular attention. It showed that a small fraction of particles carried immense kinetic energy, enough to suggest acceleration by magnetic fields. This detail revealed that even at the edge, the sun still imparts strength to its particles. It does not simply die away, it empowers. The mathematics of that curve, smooth yet surprising, became one of Voyager's most profound discoveries: that endings in space are never truly endings, only transformations disguised as silence. When the team compared these results to computer simulations, the match was uncanny. Voyager's measurements aligned almost perfectly with the theoretical models that described a pressurized, heated sheath around the heliopause. What had once been speculation became confirmation. The universe had drawn the same picture the equations had predicted, and Voyager had filled in the colors. For scientists, it was like watching an artist's sketch come to life, except the artist was nature itself, and the paint was plasma. Still, some numbers refused to fit. Certain temperature spikes defied explanation, appearing irregularly and fading just as suddenly. These anomalies, though small, fascinated researchers. They might represent passing waves from old solar eruptions, rippling across decades of distance. Or perhaps they came from the galaxy beyond, distant echoes of other stars' winds colliding invisibly. Whatever their source, they reminded everyone that data is alive, that behind each unexpected value lies a story waiting for discovery. As more readings came, the realization deepened. The boundary Voyager crossed is not an edge but a region of constant dialogue. The numbers are its words, spoken in plasma frequency and temperature shifts. Each variable interacts with the next, forming a grammar of cosmic motion. The scientists who interpret these readings are translators, turning this universal language into understanding. They know that the heliopause is not static, it's a conversation between the sun and the stars, and Voyager is listening. The total pressure values confirmed something elegant. The sum of thermal, magnetic, and dynamic pressures remained nearly constant across the transition. That balance revealed a deeper truth, that the universe loves equilibrium. No matter how wild the forces, they find harmony. The sun's push and the galaxy's pull meet perfectly, holding the boundary in place like opposing tides balancing a single wave. The math of this balance isn't just science, it's symmetry, the universe's quiet art form, expressed in digits. When viewed together, these numbers form a portrait of grace. They describe a frontier not marked by violence but by balance, not by chaos but by beauty. The data sings of cooperation between systems, of energy shared, not conquered. Voyager, through its patient sensors, captured a truth beyond language, that the cosmos thrives not in separation, but in blending. The heliopause, the heated sheath, the strange densities, all part of a larger melody of motion. The numbers are its sheet music, and the scientists, its listeners. And so, these figures, temperatures, densities, velocities, are more than scientific outputs. They are the coordinates of wonder, proof that human curiosity can stretch across the galaxy and still find rhythm in the void. The numbers make you pause because they remind you that beyond our sky lies not emptiness, but structure. They remind you that the sun still speaks, softly, through equations written in plasma and light. And somewhere, beyond where even those numbers reach, Voyager continues to listen, the small messenger who taught us how to count the warmth of infinity. When the first articles appeared describing Voyager's discovery of a hot region beyond the heliopause, the term wall of fire captured imaginations everywhere. It sounded dramatic, almost mythical, as though the spacecraft had found a cosmic barrier blazing with flame. But in truth, there are no flames in the frozen vacuum of space. What Voyager passed through was not fire in the earthly sense, but an invisible furnace made of charged particles and electromagnetic waves. The name was poetic shorthand, born from awe. Scientists themselves never called it that officially, the phrase came from storytellers, trying to translate the impossible into something the heart could picture. People are drawn to the image of fire because it represents transformation, warmth, and danger all at once. When the sun's influence fades and gives way to the interstellar medium, it feels like the edge of something, an ending and a beginning meeting face to face. To call it a wall of fire evokes a boundary that both protects and tests, a glowing border between home and the unknown. Voyager's instruments detected plasma tens of thousands of degrees hot, and though no one could see it, the description of fire fit perfectly in spirit. It captured what it felt like to stand at the edge of the sun's light. The heat Voyager sensed wasn't like the heat of a flame, licking and visible. It was a kinetic kind of heat, the energy of particles moving incredibly fast, colliding rarely but powerfully. When they spoke of this heated region, scientists described it in terms of motion and pressure, not temperature you could touch. Yet when writers heard 50,000 degrees, they imagined embers and light. That image spread from press releases to documentaries, from classrooms to bedtime stories, until the wall of fire became a symbol of the frontier itself. There's something deeply human in turning physics into poetry. Numbers are cold, but metaphors make them breathe. A wall of plasma becomes a wall of flame, a magnetic field becomes a shield, cosmic rays become invisible arrows. These transformations let us feel the science, not just understand it. The phrase wall of fire became a way of saying that even in the darkest reaches, the sun's spirit still burns, stretching out one last time before fading into galactic night. In truth, this wall is neither solid nor visible. It is a diffuse region where the solar wind slows, compresses, and heats as it meets the interstellar plasma. The particles here are so sparse that a cubic meter might hold only a handful. Yet their combined motion gives rise to energy, and that energy glows faintly in radio waves and particle counts. Voyager didn't see light, it heard the hum of that energy through vibrations in plasma frequency. That quiet hum is what inspired the fiery name, something unseen, yet alive with power. If one could somehow drift beside Voyager and look around, there would be no bright blaze, no sheet of orange flame stretching across the stars. Instead, there would be darkness, a black ocean dotted with pinpoints of distant suns. The fire would exist only in invisible radiation, a whisper of energy that can only be felt through sensors, not eyes. And still, the metaphor fits because it burns with meaning. It is fire without light, warmth without touch, a symbol of endurance in the endless cold. Writers and narrators began to use the phrase wall of fire to express what can't be easily told, that the sun's boundary is not cold indifference but an act of creation. As solar wind collides with the galaxy's breath, energy transforms, heat rises, and matter reshapes. It is an unseen alchemy, fusion's far echo. To describe it as a fiery wall isn't to mislead, but to translate the or into imagery humans can dream through. The fire is metaphorical, but the wonder is real. The wall itself, too, has meaning. It suggests separation, a line drawn between one world and another. For the sun, it marks the end of its reign. Beyond it, the Milky Way's currents rule. To cross it is to leave the solar system behind, to move from a space shaped by our star to one shaped by the galaxy. Voyager crossed that threshold quietly, yet the moment carried weight. Wall became the perfect word for what the spacecraft had passed through, a border made not of stone, but of pressure, plasma, and time. In many ways, the wall of fire is a reflection of how we think about endings. We imagine the edge of things as bright, burning, and transformative, like the horizon at sunset. Voyager's crossing marked the solar system's sunset, a transition into the interstellar sea. Calling it fire made that boundary feel alive, not empty. It reminded people that even at the farthest edge, there is still warmth, not gone, merely changed. The sun still glows there, though its light is no longer visible. The wall is not static. Voyager's readings showed that it moves and fluctuates with the sun's activity. When solar storms surge outward, the boundary swells. When the sun rests, it contracts. This living motion gives the wall an almost breathing quality. If we could see it, it might shimmer like the surface of a great flame, constantly folding, pulsing, and reshaping. So even though the fire is metaphor, The movement is real, the heliopause truly flickers in response to the rhythm of our star. Calling it a wall of fire also speaks to courage. Voyager entered that region not knowing what it would find, only predictions and hopes guided it. The spacecraft's slow, steady approach through the hot, compressed plasma mirrors a story of persistence, a tiny machine daring to move through what sounds like flame. The metaphor honors that bravery. It lets people imagine the spacecraft gliding through heat and danger, carrying humanity's message into places no living being could endure. Some poets have described the heliopause as the sun's last heartbeat, and the wall of fire as its pulse echoing outward. It's a beautiful thought that the sun doesn't end abruptly, but gently, its energy dispersing into the galaxy like embers from a dying campfire. Voyager didn't find a dead zone beyond, it found warmth, motion, and continuation. The fire wasn't destruction but persistence, the last warmth of home stretching its reach toward infinity. The phrase also resonates with ancient imagery. Fire has always been a symbol of knowledge and boundary crossing, Prometheus stealing flame, explorers sailing toward burning horizons. Voyager's story fits that lineage. Humanity lit its first fires on Earth to keep away the dark. Centuries later, it sent a mechanical flame into space to light up the unknown. When people hear wall of fire, they hear both danger and destiny, the idea that beyond every fire lies discovery. For educators and storytellers, the phrase became a bridge between complex science and public imagination. The real explanation, plasma temperatures, magnetic field transitions, particle densities, is fascinating but abstract. By calling it a wall of fire, they give listeners something vivid to hold on to, an image that lives in the mind. In classrooms and documentaries, that phrase becomes the spark that leads people to ask questions, to imagine, to learn. In that sense, the metaphor itself becomes a teacher. Scientists, though precise, aren't immune to its poetry either. Many who worked on Voyager confessed to feeling that wall of fire described the experience emotionally if not technically. They knew it was plasma, not flame, yet the phrase captured the thrill of seeing the sun's reach end in heat. It made the discovery feel human, a story rather than a statistic. Even the most disciplined researchers sometimes called the region fiery, because no other word quite carried its grandeur. There's irony in the image too. Fire consumes, but the wall of fire doesn't destroy, it preserves. Voyager passed through unscathed, continuing its long drift. The energy there is vast, but diffuse, gentle to a traveler moving at its pace. This paradox of deadly-sounding fire that causes no harm mirrors the strangeness of space itself. Things that sound fierce are often silent, things that seem empty are alive with power. The wall's flame is calm, eternal, untouchable. As Voyager continues outward, the fire fades into cooler, more stable plasma, where interstellar conditions dominate. But the spacecraft still carries traces of that heat in its data, in its recordings, in the memories of those who studied them. Each reading tells a piece of the sun's final touch, the moment it handed its traveler to the galaxy. The wall of fire marks that handoff, the gentle letting go between two vast systems. In cultural retellings, the phrase often symbolizes passage, not just physical, but spiritual. Voyager's crossing through the fiery wall is described as a soul leaving its body, or a child stepping beyond the warmth of home. It's the ultimate moment of departure, when what is known fades behind and the infinite opens ahead. The fire becomes a symbol of farewell, not an ending, but a transition into deeper silence. Even the word wall implies choice, something to approach, confront, and move beyond. Voyager didn't stop at that wall, it crossed it. That crossing turned metaphor into history. Humanity, through that small craft, touched the sun's last outpost and then left it behind. The wall of fire became our milestone, our marker in the cosmic sea, a reminder that our curiosity burns hotter than any plasma. Over time, the metaphor has taken on new meanings. To some, it represents the persistence of human warmth in the cold universe. To others, it is a reminder of boundaries we still don't understand, the unseen walls that mark beginnings disguised as ends. For many, it's simply beautiful, the thought that the sun, even at its limit, creates light where none should be. Fire, even metaphorical, feels alive. The imagery has found its way into art, music, and literature. Painters have rendered glowing veils of color, poets have described the heliopause as a burning curtain, and composers have written symphonies echoing its energy. In each creation, the wall of fire stands for transition, a cosmic sunrise in reverse. Voyager's crossing inspired a generation not only of scientists but of dreamers, all finding warmth in the idea of light surviving in darkness. For those who worked closest to Voyager, the name means something quieter. To them, the wall represents the final frontier their craft crossed before its signal began to dim. It's not the fire of drama they remember, but the fire of effort, years of design, calculation, and faith. When they say wall of fire, they think of the heat of perseverance, the glow of human hands that built a machine strong enough to touch the stars. Ultimately, the wall of fire is a metaphor that unites emotion and fact. It captures both the physics of plasma and the poetry of exploration. It is not flame, yet it burns, not solid, yet it stands. Through that name, the public found a way to feel what scientists saw, the edge of the sun's kingdom glowing softly in the dark, whispering farewell. It is the universe's most distant ember, and Voyager carried our gaze through it. The beauty of this phrase is that it turns an invisible truth into a story. Science alone might call it a heated plasma boundary, but imagination calls it a wall of fire, and both are right. For one describes the mechanism, the other, the meaning. Together, they tell a single tale, that even as we leave home, warmth follows us. Voyager proved it not with words, but with a steady signal, faint but unbroken, passing through the fire that never burns. And so, the wall of fire endures, a bridge between the measurable and the magical. It is where numbers meet wonder, where science meets story. Voyager didn't see flame, but it crossed something that felt like one, the glowing breath of our star at the edge of forever. The wall remains unseen but imagined, and perhaps that's what makes it beautiful, a reminder that even in the coldest reaches of space, there are still stories that burn softly in the dark. Out there, beyond where sunlight weakens and the solar wind falters, lies a strange kind of warmth, not the searing burn of a star, but the hush of motion meeting resistance. Voyager discovered that the heat at the boundary of the heliopause doesn't come from fire, nor from any visible glow, but from collisions so delicate they could almost be mistaken for silence. Every charged particle that drifts outward from the sun eventually finds its path slowed, nudged, and stirred by particles from the interstellar medium. The warmth born there is invisible, a soft friction written in mathematics instead of light. When we imagine collisions, we think of impacts, explosions, sparks. But in this realm, collisions are so rare that one might wait years before a single proton meets another. And yet, when they do, their meeting is powerful enough to whisper heat into the void. The heliopause becomes a place where stillness itself becomes energy, where each particle carries the memory of its long journey from the sun. The warmth Voyager sensed wasn't the roar of fire, but the gentle hum of accumulated motion, energy stored and released in slow, graceful exchanges. The plasma beyond the heliosphere is thin, so thin it defies intuition. A cubic meter of air on Earth holds trillions upon trillions of molecules, while the same volume in Voyager's region might cradle only a handful of atoms. And yet, when those few meet, the distance and time between them give their encounters weight. It's like two travelers meeting after ages of isolation, the energy of their meeting amplified by the silence that preceded it. That is where the heat comes from, not from flame, but from motion transformed into memory. Voyager's instruments picked up the evidence through vibrations in plasma frequency, faint oscillations that revealed the presence of warmth. These frequencies told scientists that the particles were not still, but vibrating with energy, heated to tens of thousands of degrees. But that number, as stunning as it sounds, is not heat in the human sense. There is no air, no burning sensation, no radiation glowing red. It is kinetic heat, the restless dance of particles that rarely meet, yet still remember how to move. Each charged particle, an ion, an electron, drifts through magnetic fields that twist and coil invisibly. These fields act like lanes on a cosmic highway, guiding motion, bending paths, exchanging energy without touch. In that magnetic ballet, heat is born without collision, as fields accelerate and decelerate particles across distances of unimaginable emptiness. Voyager detected these patterns like a stethoscope pressed to the chest of the Sun, hearing the faint rhythm of heat produced through tension rather than fire. To understand how there can be warmth without flame, one must let go of the idea of temperature as something you can feel. In deep space, temperature is not a sensation but a measure of motion. The faster the particles move, the higher the temperature, even if the environment feels impossibly cold. Voyager's sensors revealed particles zipping by at extraordinary speeds, their energy spread thin but constant. Each carries a spark of the Sun's original breath, stretched across billions of kilometers, yet still alive with movement. It is strange and beautiful that such emptiness can still produce warmth. The heat that Voyager detected was not a presence but a trace, the last murmur of the solar wind's long journey. Imagine wind traveling so far it forgets what it means to blow, until at last it meets another wind, and the two share their energy in a quiet exchange. The heliopause is that meeting place, that whispering plane of invisible touch. No flames flicker there, but something glows softly in the unseen, a warmth that never fades entirely. The collisions are called gentle not just for their slowness, but for their precision. The plasma is delicate, responsive, and elastic, moving like a tide rather than a storm. Energy is passed, not smashed. Balance is maintained rather than broken. Even in apparent chaos, the system finds equilibrium. Voyager's readings revealed this harmony through consistent plasma frequencies, proof that the collisions did not produce violent shocks, but a smooth and steady hum. The boundary of the Sun is less a battlefield than a quiet negotiation. If one could somehow float beside Voyager and watch the invisible play of forces, the scene would be motion without sound, waves rippling through space, bending, merging, dissolving. The heat, invisible to the eye, would shimmer like ripples on a pond. There would be no firelight, no glow, only a feeling of continuous, patient energy. This is the paradox of the universe's edge. Stillness becomes motion, emptiness becomes warmth, and collisions too small to see sustain heat large enough to be measured across billions of kilometers. The particles themselves come from two sources, the solar wind and the interstellar flow. The solar wind carries protons and electrons launched from the Sun's corona, while the interstellar medium brings atoms from other stars. When these two rivers meet, they don't crash like waves, they mingle, exchanging charge and motion. Each interaction adds a flicker of heat, a spark without flame. Over time, those tiny exchanges weave a zone of subtle warmth, a sheath of quiet energy marking where one domain ends and another begins. Voyager's instruments, designed decades earlier, were never meant to detect such faint signals, and yet they did. The plasma wave detector, in particular, became a translator of silence, turning the faint hums of charged motion into audible frequencies. To scientists, those sounds became proof of heat where no heat should be. Each pulse was a signature of movement, a sign that the Sun's breath still stirred matter far beyond its light. These gentle collisions were the heartbeat of a boundary once thought frozen. Somewhere in those numbers, a story unfolded, of balance between opposites, of two forces that do not destroy but transform one another. The heliopause became not a line of separation, but a zone of translation, a cosmic twilight where solar energy becomes galactic warmth. The collisions there are the smallest imaginable, but their sum is grand, a harmony so vast it envelops the solar system itself. Voyager's sensors, listening patiently, captured that harmony and sent it home across the dark. The absence of visible fire also teaches a lesson about how nature hides its brilliance. The universe doesn't always announce its power through light. Sometimes it works in vibration, in pressure, in frequency. Voyager's crossing revealed that the space between stars is not dead, but alive with invisible energy. The gentle collisions that feed this energy are too soft to illuminate, but too constant to ignore. In their quietness lies their strength, a warmth that requires no flame to endure. When scientists analyzed the data, they realized the energy balance was nearly perfect. The pressure from the solar wind and the resistance from the interstellar medium were almost equal, creating a smooth transition instead of a violent boundary. This equilibrium explains why the heat doesn't flare into chaos. It spreads evenly, calmly. The heliopause isn't a wall, it's a veil, soft, shimmering, and stable. Through it, heat flows like breath, carrying the echo of a star's heartbeat into the galaxy. In this region, magnetic fields are the invisible threads weaving the fabric of warmth. Each charged particle follows these lines, spiraling and dancing in perfect geometry. The collisions, when they happen, are guided by these patterns, turning chaos into choreography. Voyager's instruments traced these paths indirectly, finding beauty in the precision. The plasma's behavior was not random, it moved with a kind of discipline, shaped by forces both local and cosmic. The warmth was an order disguised as drift. The term heat without flames might sound paradoxical, but in space, it is the norm. Fire, as we know it, requires air, oxygen to feed on. Out there, in the deep dark, there is no oxygen, no burning. And yet, motion persists, energy transfers, warmth exists. What Voyager discovered was a kind of cosmic smoldering, a field where motion and magnetism combine to keep the void alive. It is the gentlest fire there is, one that consumes nothing and sustains everything. Each time Voyager transmitted new data, scientists could see the subtle signatures of these interactions: slow waves, long delays, faint increases in plasma frequency. These signs told them the spacecraft was moving through a zone of sustained, invisible warmth. The longer it traveled, the clearer the pattern became. The sun's influence didn't end sharply but faded gradually, each kilometer bringing a slight decrease in heat. Like walking away from a bonfire you can no longer see but still feel. Some theorists suggested that the heat persists because of turbulence, miniature storms of magnetic energy that churn gently through the plasma. These eddies, though tiny compared to galaxies, are vast on a human scale, each spanning thousands of kilometers. Within them, particles are constantly accelerated and slowed, trading momentum endlessly. That constant trade keeps the plasma warm, even when no new energy arrives. It is the physics of continuity, warmth sustained through perpetual motion, not ignition. The phrase gentle collisions also reflects how time itself moves differently there. In that sparse environment, events unfold slowly. A reaction that takes milliseconds on Earth might take centuries in deep space. Voyager's sensors, built to outlast their makers, became patient observers of these slow dances. Over years, they watched the same patterns shift by fractions, listening as eternity unfolded in increments. The spacecraft had become a witness to cosmic stillness moving at the pace of thought. The warmth Voyager recorded isn't just a physical phenomenon, it carries symbolic weight. It shows that even in the most desolate reaches, there is connection, interaction, and transformation. The sun and the galaxy do not turn away from each other, they meet and share energy softly. That exchange is the essence of continuity, the way the universe ensures that no boundary is truly an end. The Heliopause's heat is the handshake between two infinities. If we were to translate those collisions into human sensation, they might feel like the faintest vibration on the skin, the whisper of distant wind. There is no sound in that space, yet its energy resonates. The warmth is not physical but emotional in its message, proof that motion continues, that the sun's touch lingers. Voyager's recordings of plasma waves have even been converted into audio, and when played, they sound eerily alive, like the breathing of the universe itself. The collisions may be gentle, but their effects ripple far. The slight heating influences the flow of cosmic rays, shapes the magnetic field, and determines how particles move into and out of the solar system. This subtle balance protects us, bending high-energy radiation and softening its blow. The warmth Voyager found isn't isolated, it's part of the invisible barrier that shields life on Earth from galactic storms. The gentle collisions, in their quiet way, help sustain everything we know. In the end, what Voyager revealed is that heat doesn't always roar. Sometimes, it whispers. Sometimes, it's not born of destruction, but of meeting, of things moving together rather than apart. The warmth beyond the heliosphere is an act of cooperation, not combustion. It shows that even in emptiness, interaction thrives, and that even without flame, there can be fire's essence, transformation, persistence. Light unseen. Each piece of data Voyager sent home carries that lesson. Every oscillation recorded, every small rise in plasma frequency, speaks of motion continuing quietly in the void. The spacecraft itself now floats within that warmth, its metal body bathed in invisible energy, its signal stretching back across the dark. Through it, we learn that the universe's most enduring fires are the ones that do not burn, the gentle collisions that give life to silence. And so, beyond the reach of sunlight, Voyager sails through a furnace of stillness, a sea of warmth without light. The gentle collisions that surround it are soft reminders that nothing is ever truly cold in the universe, not motion, not time, not even the end of a star's breath. There are flames here, unseen and eternal, born from the grace of particles meeting in peace. It is the quietest fire imaginable and the most enduring. At the far edge of the sun's reach lies something almost alive, a membrane of invisible motion that swells and contracts, like a lung exhaling softly into the void. This thin layer, where the solar wind meets the whispering pressure of the galaxy, doesn't remain still. It breathes in response to the sun's moods, expanding when its wind grows fierce, retreating when its energy wanes. Voyager drifts through this pulse, sensing the faint rise and fall of a living boundary that separates our sun's domain from the dark sea beyond. The heliopause is not rigid or flat, it quivers, flexing like the surface of a heartbeat. Each solar storm that travels outward from the sun pushes against it, causing ripples to spread across its structure, invisible yet powerful. Voyager's instruments pick up the tremors of this boundary, fluctuations in magnetic field, changes in plasma density, like the slow rhythm of breathing. It is not the breath of a creature, but of a system, an entire solar bubble inhaling and exhaling in cosmic time. Inside this vast shell, the solar wind dominates. Outside, the interstellar medium presses back. The thin layer where they meet is neither wholly one nor the other. It's a place of blending, of mingling energies. Charged particles slow down, exchange heat, and change direction. Fields twist and reconnect. Each movement transfers energy, like air passing through a lung's membrane, not in flames, but in flow. Through these exchanges, the solar system maintains balance with the galaxy that surrounds it. When Voyager crossed into this breathing zone, it detected waves in plasma frequency, low hums that changed pitch, like a sigh-shifting tone. Scientists realized these were ripples in the thin plasma sheet, caused by the push and pull of solar activity. The heliosphere was not static at all, it was dynamic, flexible, sensitive to every pulse of energy from the sun. The thin layer was alive with motion, an unseen lung stretching and contracting with every solar heartbeat. This understanding transformed how we imagine the boundary of our solar system. It is not a sharp edge or a frozen frontier, but a breathing skin, a region where the sun's influence meets the galaxy's touch in constant negotiation. Voyager became the first witness to this breathing, its instruments recording every sigh. The temperature rose, then steadied. The density changed, then recovered. Like a lung adjusting to each breath, the heliopause moved in cycles, never resting, always alive in its slow rhythm. In some ways, this behavior mirrors life itself. Every organism maintains balance with its surroundings through exchange of air, of heat, of energy. The sun and the galaxy do the same. The solar wind carries particles outward, the interstellar medium pushes back. Their contact forms a zone of trade, where heat and motion are balanced. To call it breathing is poetic, but not untrue. It is the slow respiration of cosmic scales, where physics becomes rhythm and movement becomes melody. The layer's thinness is deceptive. Though it may span billions of kilometers, it is still only a tiny fraction of the solar system's total reach. Within that span, particles collide rarely but meaningfully. Each impact transfers a whisper of energy, shaping the magnetic texture of space. Voyager's sensors detect these whispers as subtle fluctuations, tiny variations in plasma waves that speak of temperature and density. From these small shifts, scientists read the pulse of the heliopause like a doctor listening through a stethoscope. When solar storms reach the heliopause, they compress this breathing layer. For a time, the solar bubble tightens, its edge pushed outward by the storm's momentum. Then, as the storm passes, the pressure drops and the layer relaxes again. Voyager experiences these changes as distant tremors, the soft contraction and expansion of a system inhaling and exhaling light years from home. These motions may take months or even years, but to the sun and the galaxy, they are as natural as breathing. Within this region, magnetic reconnect ion plays a vital role. When the sun's magnetic field lines encounter those from interstellar space, they can break and reform, releasing bursts of energy. This invisible interaction acts like a heartbeat within the breathing pattern, injecting warmth and turbulence into the thin layer. Voyager recorded such events, detecting sudden shifts in direction and strength of magnetic fields, proof that the heliopause was not just a passive wall, it was active, reacting to its environment like a living thing. The thin layer also moderates the flow of cosmic rays. When the heliosphere contracts, more galactic particles can penetrate deeper into our system. When it expands, fewer make it through. This breathing action subtly affects the radiation environment near Earth, reminding us that the sun's invisible lung has consequences across all space within it. Voyager's data helped reveal this connection, how far away pulses influence the airless space that still protects our fragile world. To imagine this layer, one might picture the surface of a soap bubble drifting through the wind. It glimmers, flexes, and shifts, always reshaping itself against the surrounding air. The heliopause behaves much the same, though its air is made of charged plasma instead of molecules. Like a bubble, it can wobble, oscillate, and ripple when struck by force. Voyager's steady passage through this film captured a living image of cosmic balance, fragile yet vast, delicate yet powerful. The breathing rhythm of this layer is slow compared to any human sense of time. Each full inhalation or exhalation may take years, shaped by the sun's 11-year magnetic cycle. During times of high activity, when the sun releases more flares and winds, the heliosphere expands, puffing outward like a deep breath. In quieter years, it contracts. Voyager's measurements show that this rhythm echoes through space, reaching even beyond the sun's grasp. It is a cycle written in plasma and light. Though the analogy of breathing is poetic, the physics behind it is precise. Pressure waves, magnetic tension, and plasma flow all combine to create oscillations in density and temperature. These oscillations travel through the boundary like sound through air. Voyager's instruments record their passing, translating them into data that, when plotted, reveal the heartbeat of the heliopause. What we see is not chaos but harmony, a self-regulating system adjusting to the push and pull of cosmic forces. In this thin layer, time moves differently. The signals Voyager receives from the Sun take over 20 hours to arrive, while the effects of a solar flare may take years to reach its surroundings. Everything happens in slow motion, yet with exquisite precision. The breathing continues whether we observe it or not, like the steady rhythm of sleep in a resting body. It is a kind of serenity, the quiet mechanics of existence scaled up to the size of the solar system. When scientists studied Voyager's recordings, they noticed subtle patterns in the data, faint fluctuations that repeated at intervals matching the Sun's cycles. These were the breaths of the heliosphere, recorded in soundless form. To translate them into human perception, researchers converted them into audio frequencies. What emerged was an eerie hum, rising and falling with the motion of the plasma. Listening to it was like hearing the exhalation of a giant invisible being resting among the stars. As Voyager moved farther from the Sun, it entered a region where this breathing slowed. The pressure of interstellar space began to dominate, damping the solar wind's rhythm. Yet even there, the memory of the Sun's breath remained, a faint pattern still imprinted on the particles drifting outward. Voyager was leaving the lung, stepping into the space beyond it, where the flow of the galaxy would take over. The transition was gentle but final, the quiet ending of a long exhale. The thin layer's existence also helps us understand how stars interact with one another. Every star in the galaxy creates its own bubble of influence, surrounded by a boundary where its wind meets interstellar gas. Each of these bubbles breathes, shifts, and flexes as its parent star changes. Voyager's findings give scientists clues about how other stellar systems live and evolve. By studying the Sun's lung, we learn about the life breath of the cosmos itself. The heliopause's breathing may even influence the shapes of cometary paths and cosmic dust streams entering the solar system. As the layer expands and contracts, its magnetic and electric fields shift, subtly altering the trajectories of charged particles. These small effects ripple inward over time, shaping the fine balance of forces that fill interplanetary space. In that sense, every breath of the Sun's boundary gently stirs the fabric of the solar neighborhood. It's strange to think that something so vast can be so delicate. A motion measured across billions of kilometers feels fragile, but that fragility holds power. Through balance and exchange, the heliopause maintains order in the face of galactic chaos. Without it, cosmic rays would strike harder, solar particles would escape farther, and the solar system's boundaries would dissolve into the interstellar sea. It is a breathing wall that sustains the rhythm of space around our Sun. For Voyager, this breathing frontier was both destination and doorway. Each pulse of plasma it recorded added to a symphony of data that continues to play across scientific papers and classrooms. The spacecraft could not see the lung itself, but it felt every motion, every quiver. And through it, we came to understand that our Sun does not simply radiate, it interacts, it exchanges, it lives in conversation with the galaxy. The idea that the Sun's edge breathes like a lung changes how we see our place in the universe. It reminds us that boundaries are never absolute, they are points of contact, of exchange. Just as the air we breathe connects us to life on Earth, the plasma our Sun exhales connects us to the galaxy. Voyager, crossing through that thin layer, became the messenger of this truth, that the cosmos is not silent or still, but alive in its own vast rhythm. Even now, the data Voyager sent continues to breathe in another way through our minds. Each discovery expands and contracts our understanding, as knowledge flows between what we know and what we still dream of finding. The thin layer at the sun's edge is both physical and symbolic, the boundary between ignorance and wonder, between science and poetry. And in that space, we find not separation, but connection. So the lung of the sun continues its slow respiration, unseen but ever present. Its breaths reach beyond the edges of planets and light, touching the quiet beyond where Voyager drifts. And though the spacecraft has moved far from that layer now, it carries the sound of those breaths within its data, a gentle, endless whisper of balance between the star that gave us life and the galaxy that holds us all. At the farthest edge of the sun's reach, where the solar wind sighs into stillness, something unseen holds the shape of everything. It is not matter, not heat, but lines of invisible force, magnetic threads, woven together like the fibers of a cosmic fabric. They cross, twist, and fold upon one another, creating the boundary that Voyager drifted through. These are the sun's magnetic field lines, stretched, thin by distance, yet still pulsing faintly with the rhythm of the star that birthed them. The heliopause is not simply a wall of plasma and particles, it is a magnetic tapestry. Within it, fields from the sun meet those of the galaxy, interlacing like threads from two vast looms. Each line carries direction, tension, and memory, a record of its origin. The sun's magnetic strands spiral outward in the shape of the Parker spiral, created by the sun's rotation. The interstellar fields approach at odd angles, like waves striking a shore. Where they meet, they don't simply merge, they weave. Voyager's magnetometer detected this weaving not as pictures, but as subtle shifts in the direction and strength of fields. These tiny variations told scientists that the spacecraft was crossing zones where the sun's field gave way to the galaxy's. It was like moving from one cloth into another, not with a tear, but through a region where the threads of each overlapped. The border between solar and interstellar space turned out to be a blend, not a barrier. The beauty of this structure lies in its fluidity. Magnetic lines are not rigid, they flow, bend, and reconnect. When opposing fields meet, they can break and reform, a process called magnetic reconnect-ion. It's like two ropes untying and knotting themselves anew, releasing stored energy as they do. Voyager's instruments caught signs of this happening at the edge, faint bursts of plasma heat and sudden changes in field direction. Each reconnect ion was a spark in the invisible fabric of space. The sun's field lines, carried outward by the solar wind, form enormous loops and spirals that fill the heliosphere. As they stretch farther, they thin and lose strength, but their pattern remains. The interstellar magnetic field, older and broader, approaches from outside like a vast current pressing against the bubble. When the two meet, they do not clash violently. Instead, they entwine. The result is a sheath of twisted strands, a border that is alive with motion. This woven region acts as a filter. Charged particles from the galaxy encounter these tangled lines and are deflected or slowed, while some from the sun slip outward along narrow channels between them. The magnetic fabric thus shapes how energy and matter pass in and out of the solar system. Voyager's data helped reveal this intricate choreography, where the sun's influence fades not abruptly but through a complex dance of weaving lines. In places, the threads align. When the sun's magnetic field happens to match the direction of the interstellar one, the two merge smoothly, creating corridors of passage through which particles can travel more easily. In other places, they oppose each other, forming knots of resistance that block flow and build pressure. Voyager detected both regions of harmony and regions of tension, like alternating patterns in a woven cloth stretching across billions of kilometers. These magnetic threads do more than define the border, they hold memory of motion. Each carries traces of solar storms that once surged through space, their energy now stretched thin across the edge. When such storms reach the heliopause, they tug on the fabric, causing ripples that travel outward like waves in silk. Voyager's sensors recorded these ripples, revealing that even at such extreme distances, the sun's past breath still stirred the border's magnetic web. The interstellar medium, too, contributes its own threads. Its magnetic fields are shaped by ancient events, the shockwaves of supernovae, the birth of distant stars, the quiet drift of galactic clouds. When these fields touch the heliosphere, they add new strands to the weave. The result is a border stitched from history itself, part solar, part galactic, a meeting place of two enormous stories written in lines of invisible force. This magnetic weaving has an elegance that no human hand could design. It balances tension and flow, resistance and harmony. Where lines reconnect, heat blooms. Where they align, calm prevails. Voyager, drifting through this complex border, became a silent observer of a living network, a web that breathes energy from both the sun and the stars beyond. Through its measurements, we glimpse the threads of creation itself, the unseen architecture that holds space together. Scientists often describe magnetic fields mathematically, with equations and vectors. But here, at the edge of the sun's realm, those equations take on the grace of art. The interactions are too vast and too fluid to visualize completely, yet the image of woven threads captures something essential. The heliopause is not a surface, it's a fabric stretched across the void, where each line hums faintly with the story of its journey. When the solar wind presses outward, it stretches these threads taut. When the interstellar medium pushes back, they loosen and twist. The entire structure flexes and shimmers, responding to forces that change slowly over years. Voyager's instruments are like fingertips brushing this vast web, feeling the vibrations of magnetic music that plays without sound. Through it, we sense how the sun breathes into the galaxy not only with particles, but with fields. One of the most remarkable discoveries from Voyager's journey was the direction change of magnetic fields after it crossed the heliopause. Scientists expected a sharp shift from the sun's field to the galaxy's, but the transition was smooth. The angle shifted only slightly, as though the two fields were gently woven together. This hinted that the sun's magnetic influence extends farther than expected, blending with the galaxies in quiet continuity rather than sharp division. The image that emerges is one of unity, not separation. The magnetic border is not an obstacle but a connector, binding the solar system to the galaxy. Energy flows through it constantly, in the form of charged particles spiraling along the threads. These motions carry information, shaping cosmic rays, plasma waves, and even the faint radio hums that Voyager still detects. The heliopause is, in essence, the sun's handshake with the Milky Way. To imagine this weaving on human terms is nearly impossible. Each magnetic strand can stretch millions of kilometers, yet is finer than the air between atoms. Their intersections create turbulence on grand scales, eddies and swirls where charged particles are accelerated to immense speeds. Some of these accelerated particles travel back inward, eventually reaching Earth as cosmic rays. The sun's magnetic fabric, then, subtly connects our skies to the galaxy's fields. The energy released by magnetic reconnect ion at this border may also heat the plasma, explaining why Voyager found temperatures so unexpectedly high. These reconnect ions act like sparks where threads rub together, converting magnetic tension into thermal energy. But the heat is not like a flame, it's the glow of motion, the friction of invisible forces turning into warmth. The heliopause's temperature, tens of thousands of degrees, is born from these magnetic knots untangling themselves. Even though magnetic fields are intangible, their effects shape everything. They guide particles, sculpt space, and define the edges of influence. Without them, the solar wind would disperse aimlessly, and the interstellar medium would press unopposed. The border would collapse, and the sun's bubble would fade. Instead, the magnetic threads hold the system together, forming a breathing boundary that endures across millions of years. As Voyager continued its journey, the sun's magnetic threads stretched thinner, their presence slowly fading beneath the stronger pull of the galaxy's field. The spacecraft drifted from the woven region into a realm dominated by interstellar magnetism. But even there, echoes of the sun's field remained, faint but measurable. It was as if a few golden strands still clung to Voyager, whispering the sun's touch across the dark. In this woven border, the laws of physics become poetry. The constant interplay between pressure and tension, flow and resistance, speaks of balance rather than conflict. The sun and the galaxy are not fighting for space, they are dancing in equilibrium. The magnetic threads that connect them act like the fabric of a shared breath, one that stretches across the cosmos with both gentleness and strength. Each solar cycle changes the weave. When the sun's polarity flips every 11 years, its field lines twist differently, altering how they meet the interstellar field. The border's pattern shifts accordingly, as though the tapestry were being rethreaded. Voyager's continuous data helps trace this slow reweaving, giving scientists a moving picture of how the solar system's skin renews itself in rhythm with the sun's changing heart. What Voyager saw, though invisible to the eye, was a grand piece of cosmic embroidery. Every variation in its readings hinted at unseen loops, folds, and crossings. The spacecraft's slow passage through them gave humanity a glimpse of how space itself is held together not by matter alone, but by forces that thread through emptiness. These magnetic strands, delicate and immense, weave order into what might otherwise be chaos. Beyond the poetry lies practical truth. Understanding how these threads behave helps scientists predict how cosmic rays enter the solar system, how magnetic storms affect our technology, and how interstellar plasma behaves near stars. The Heliopause's fabric is a microcosm of galactic processes. What happens here also happens around other suns, other systems, perhaps even those hosting worlds like ours. It is humbling to think that Voyager, a machine no larger than a car, floated through such complexity. Its sensors, designed decades ago, traced the threads of a structure billions of kilometers wide. From those faint signals, we now understand that the edge of our solar system is not a void but a woven boundary, rich with motion and meaning. The spacecraft has become a needle, stitching our awareness into the fabric of the galaxy. The magnetic threads at the sun's border continue their ceaseless weaving. They stretch, reconnect, vibrate, and evolve in silence. Each motion contributes to the music of the cosmos, unheard but ever present. Voyager, far away, still listens to the echoes of that song, sending home whispers of the pattern that holds everything together. And in its data, we find proof that even the emptiest places are not empty at all, they are woven with invisible threads of connection. Voyager carries with it instruments designed more than 4 decades ago, yet their performance has outlived expectations. Built in an era when computers were room-sized and data storage was minimal, each sensor is remarkably precise, tuned to capture the faintest whispers of space. These old hands, plasma detectors, magnetometers, and plasma wave receivers now serve as translators for the unknown, recording interactions that no one in the 1970s could have fully imagined. They have become bridges between human foresight and the galaxy's secrets. The plasma detector, one of Voyager's earliest instruments, measures the density and speed of charged particles. It was designed for the solar system's planets, yet beyond Neptune, it revealed something entirely new. As the spacecraft approached the Heliopause, the detector sensed particle densities far lower than anticipated, yet temperatures far higher. These readings suggested that the solar wind, though thinning, continued to interact with interstellar plasma in ways invisible to the eye, a subtle energy dance Voyager recorded with meticulous care. Magnetometers, though comparatively simple in design, have become essential in mapping the sun's fading magnetic field. By measuring the strength and direction of magnetic lines, scientists have reconstructed the invisible threads weaving the Heliopause. Voyager's magnetometers detect slight fluctuations that reveal reconnect ion events, where magnetic lines break and reform, converting energy into particle motion. The readings are delicate yet revealing, providing a detailed map of the dynamic boundary between solar and galactic influence. The plasma wave instrument, perhaps the most poetic of Voyager's sensors, translates the vibrations of charged particles into audible signals. Each spike and hum represents a ripple in space itself, a subtle note in the orchestra of the heliosphere. Through these recordings, scientists detected the heated region beyond the sun's influence, the so-called wall of fire. The instrument turns the invisible into sound, allowing humanity to listen to the motion of particles we cannot otherwise see, bridging perception and physics in one elegant design. Voyager's instruments work slowly but persistently. Data is not instantaneous, signals take hours to reach Earth, and bandwidth is minimal. Yet despite these constraints, the spacecraft continues to return a wealth of information, proving that age does not limit insight. Each packet of data contains not just numbers, but evidence of phenomena previously theorized but never observed. The old hands of Voyager provide humanity with fresh eyes on the frontier, allowing discoveries far beyond their original purpose. Temperature measurements, once thought straightforward, became revolutionary in the outer heliosphere. Voyager detected plasma with temperatures tens of thousands of degrees higher than expected. The instruments revealed that collisions between particles, though rare, produce a surprising heat through kinetic energy transfer. This subtle heat, invisible yet immense in scale, was the first indication of the sun's influence stretching into the interstellar medium, a revelation that reshaped our understanding of the boundary of the solar system. Voyager's cosmic ray instrument, designed to study energetic particles near planets, now serves a different role, monitoring the flux of galactic cosmic rays entering the solar system. The data show fluctuations influenced by the sun's magnetic field and the Heliopause's dynamics. By observing these changes, scientists can trace how the boundary filters radiation, protecting planets within the heliosphere. This information is vital for understanding both space weather and the environment that future explorers will encounter. The magnetometer readings revealed a subtle surprise. The transition from the solar magnetic field to the interstellar field was not abrupt. The old instrument detected only a slight rotation in direction, suggesting that the two fields interlace and blend rather than clash violently. This smooth transition, invisible to the eye but clear in Voyager's data, underscores the sophistication of the spacecraft's design. Sensors built for planetary study now reveal the nuanced choreography of magnetic fields at the solar system's edge. Even after decades of cosmic radiation, exposure and extreme temperatures, Voyager's instruments remain remarkably stable. Their calibration has held through intense solar flares, the vacuum of space, and the cold beyond Pluto. Each measurement is a testament to human engineering, devices built with foresight, redundancy, and simplicity, able to persist where more complex technology might have failed. These instruments are old hands that have grown wise through experience, witnessing the unknown with unwavering fidelity. The cosmic dust detector, though often overlooked, also contributed to the story. It records tiny grains that traverse the heliosphere, giving clues to particle motion in the solar wind and beyond. By analyzing how these grains respond to magnetic fields, scientists can infer properties of the thin layer at the heliopause. Voyager's data reveal how dust interacts with both solar and interstellar environments, offering a tangible way to sense otherwise invisible processes in the vast emptiness of space. Voyager's imaging systems, while no longer capable of taking pictures at this distance, played a crucial role early on by mapping planetary atmospheres and moons. The precision engineering of these cameras ensured that even when unused now, the supporting systems, sensors, and data handling mechanisms contribute to the spacecraft's ongoing observations. In effect, the legacy of Voyager's eyes allows the other instruments to function efficiently, preserving the integrity of each measurement sent back to Earth. The spacecraft's power system, based on radioisotope thermoelectric generators, has steadily declined yet remains sufficient for these delicate measurements. The old hands of the instruments rely on this quiet, enduring energy source to maintain functionality. Each signal sent across billions of kilometers is a testament to both Voyager's resilience and the ingenuity of its designers. Without this reliable power, the precise readings of plasma waves, magnetic fields, and cosmic particles would cease, leaving the border unobserved. One of the remarkable aspects of Voyager's instruments is their ability to adapt to unexpected phenomena. Though not designed for the interstellar medium, the detectors successfully captured particle density fluctuations and high-energy plasma beyond the heliopause. The spacecraft continues to provide real-time information about the interactions between the Sun's outflow and the galaxy's background, revealing patterns that scientists could only hypothesize decades ago. In this way, old technology achieves new discoveries. Voyager's data also help refine models of particle acceleration in space. By tracking the energy and direction of cosmic rays and solar wind particles, the instruments reveal how the heliopause acts as both barrier and conduit. Reconnect ion events, magnetic turbulence, and plasma waves observed through these sensors illustrate the delicate mechanisms by which particles gain energy, reshaping our understanding of how stars interact with their surrounding environments. Temperature spikes detected by the plasma detector suggest microscale turbulence at the heliopause. Each minor collision, though statistically rare, contributes to the overall heating of the plasma. Voyager's instruments measure these variations with such precision that scientists can map energy transfer across a vast boundary in real time. It is as though the spacecraft has become a thermometer for an invisible furnace, recording the subtle warmth born of countless gentle interactions. The longevity of Voyager's instruments allows for unprecedented temporal analysis. Measurements taken decades apart reveal how solar activity propagates outward, influencing the heliopause over years. This long-term perspective is unique in science, providing insight into processes that unfold far more slowly than a human lifetime. The spacecraft becomes a time machine, recording the slow evolution of boundaries shaped by both the Sun and the galaxy. Voyager's magnetometer and plasma instruments work in tandem to reveal the interdependence of fields and particles. Fluctuations in magnetic lines correspond to changes in plasma density, demonstrating the intricate feedback between motion and force. These observations validate theoretical models while uncovering surprises, showing that even at enormous distances, the heliosphere behaves as a coherent system, responsive to both solar and interstellar influences. Cosmic ray variations observed by Voyager also provide information about the shielding effects of the heliosphere. The instruments detect increases in galactic cosmic rays as the spacecraft moves beyond the Sun's protective bubble, illustrating the role of the thin layer at the boundary in moderating radiation. The old instruments thus become vital tools for understanding planetary protection, revealing the heliosphere's function as a silent guardian against energetic particles. Despite decades of exposure to interstellar conditions, Voyager's instruments maintain remarkable sensitivity. They can detect variations in plasma density of just a few particles per cubic centimeter and magnetic field changes of mere nanoteslas. These subtle measurements are the fingerprints of the Sun's influence at the very edge of its domain, recorded with patience and precision by technology conceived when humanity had barely left Earth orbit. The spacecraft also records energetic electron bursts, sudden spikes caused by interactions between solar wind and interstellar magnetic fields. The plasma wave instrument captures these bursts as oscillations, transforming invisible energy into measurable signals. Each detection provides evidence of the complex dance at the boundary, where the Sun's breath meets the galactic current, and where Voyager's instruments translate motion into knowledge. Voyager's sensors reveal that the heliopause is not a static barrier but a living, flexible environment. Its magnetic fields, plasma densities, and particle flows fluctuate continuously. The instrument's ability to track these changes across years demonstrates their resilience and precision. Each reading, transmitted back to Earth, is a testament to how well-crafted, older technology can uncover the deepest mysteries of space, bridging decades between design and discovery. The spacecraft's suite of instruments also allows for cross-verification of data. Plasma detectors, magnetometers, and wave instruments confirm one another's readings, providing confidence in the interpretation of subtle phenomena. When a temperature spike aligns with a magnetic fluctuation and a change in particle flow, scientists can reconstruct events with remarkable accuracy. Voyager thus becomes more than a machine, it becomes a storyteller, revealing the narrative of space in signals and numbers. Old instruments, new discoveries, that is the essence of Voyager's journey. Each sensor, designed in an era before the outer solar system's boundaries were known, continues to expand our understanding of space. They capture data on plasma heating, magnetic threading, cosmic ray flow, and subtle particle interactions. Through their continued operation, they prove that foresight, precision, and durability can allow human-made technology to reveal secrets that could not have been imagined at the time of creation. Voyager's instruments are living witnesses to change. They track the fading influence of the Sun, the encroachment of galactic fields, and the complex interactions at the Heliopause. Even decades after launch, they record data that challenge assumptions and refine models of space physics. The old hands of Voyager act with the wisdom of experience, sensing phenomena far beyond their original purpose, showing that even aging technology can remain a pioneer. The ability of Voyager to send this information across billions of kilometers is in itself extraordinary. Data transmitted over vast distances are weak and subject to interference, yet the instruments continue to deliver precise readings. Each packet of information represents both the endurance of the spacecraft and the ingenuity of its creators, allowing humanity to peer into the unseen reaches of space and understand boundaries that exist only as fields, particles, and subtle energy flows. Even as Voyager drifts farther into interstellar space, the legacy of its instruments continues. They allow scientists to track plasma density, magnetic field direction, cosmic ray intensity, and wave frequencies, building a comprehensive picture of the Heliopause and beyond. Their continued operation transforms our understanding of the Sun's influence, revealing a dynamic, breathing, magnetically woven frontier that defines the outermost edge of our solar system. Voyager's instruments, though simple by today's standards, demonstrate the value of reliability and precision. They prove that carefully designed tools can continue to provide groundbreaking discoveries long after their creation. The spacecraft sensors have taught us about gentle particle collisions, invisible heat, magnetic weaving, and the protective role of the heliosphere. They are reminders that age does not diminish insight, and that curiosity coupled with thoughtful engineering can illuminate the farthest reaches of the cosmos. Voyager did not melt because, paradoxically, it traveled through space almost entirely devoid of matter. There is no atmosphere to ignite, no oxygen to fuel combustion, no friction to generate the heat that would consume objects on Earth. The vacuum of space is a near-perfect insulator. Even as Voyager drifted through regions of plasma heated to tens of thousands of degrees, the particles are so thinly distributed that collisions are extraordinarily rare. Each proton or electron carries energy, but the chance of enough particles hitting the spacecraft at once to cause melting is effectively zero. The warmth Voyager's instruments detected beyond the Heliopause is misleading in terms of danger. Temperature in space is not the same as temperature on Earth. It is a measure of particle motion, not a sensation that can scorch a material. In the region of the Heliopause, there might be thousands of degrees Kelvin, but those degrees exist in particles separated by vast distances, kilometers, even millions of kilometers apart. The probe is not bathed in a fluid medium that can conduct this heat. Essentially, it can move through a furnace without touching the flames. Thermal design also played a critical role in Voyager's survival. Engineers encased the spacecraft in layers of insulation and reflective coatings. The electronics are housed within a compartment that retains heat from the radioisotope thermoelectric generator, maintaining operational temperatures in the extreme cold of space. This thermal control system prevents both freezing and overheating, allowing instruments to function across the varied conditions encountered from launch to interstellar space. The radioisotope thermoelectric generator itself produces heat in a controlled way. Plutonium-238 decays naturally, releasing energy over decades. This energy is converted to electricity, but the residual heat is absorbed by the spacecraft structure, slowly radiating into space. Voyager's designers understood that the probe would encounter cold as well as rarefied heat, and built in this slow, steady internal warmth to keep circuits within operational tolerances, ensuring the spacecraft could survive where thermometers might read extreme numbers without it melting. Another factor is the nature of plasma collisions. The particles Voyager encountered at the Heliopause move incredibly fast, yet the density is minuscule. Kinetic energy is high on a per-particle basis, but the probability of many particles striking the same area simultaneously is infinitesimal. In other words, each particle is like a snowflake hitting a wall at extreme speed, individually energetic, but collectively incapable of causing melting. This rarefied interaction preserves the integrity of Voyager's hull and instruments. Radiation also plays a role in perception. Voyager moves through solar and cosmic radiation, yet the probe's shielding and design prevent damage from thermal effects. High-energy particles can dislodge atoms from materials, causing slow erosion over decades, but they do not generate heat in the way that combustion or friction does. The spacecraft's aluminum skin and electronic enclosures are chosen for their resilience to both radiation and vacuum, allowing the probe to drift through energetic regions without structural failure. Heat conduction requires contact. On Earth, a flame melts metal because energy is transferred continuously from particle to particle. In interstellar space, Voyager is mostly alone in a vacuum, and the plasma around it is not dense enough to conduct significant heat. The few particles that do collide with its surface transfer negligible energy in terms of temperature rise. Any heat generated is instantly radiated into the vast surrounding space, maintaining equilibrium. The probe, in essence, floats untouched in a high-energy but near-empty medium. The spacecraft's instruments are built for extremes. Electronic components operate in vacuum and at temperatures ranging from deep cold to modest warmth from internal decay. Materials are selected for their low thermal expansion and radiation resistance. The wiring, sensors, and circuit boards can tolerate both thermal and kinetic stress, ensuring that even as plasma moves past at high velocity, nothing warps, burns, or melts. Every detail reflects forethought for longevity in space's harsh but deceptive environment. Even micrometeoroids pose little risk of heat damage. Collisions with small particles generate energy, but these events are infrequent and localized. The spacecraft's geometry minimizes exposed surfaces, and redundant systems ensure continued function if minor damage occurs. Unlike Earth's atmosphere, where friction converts high-speed entry into intense heat, Voyager moves in vacuum, so kinetic energy does not translate into melting or widespread thermal stress. The illusion of danger arises from our intuition. We equate thousands of degrees with burning metal, but space is counterintuitive. A particle's temperature does not directly translate into heat transfer. Voyager's speed relative to the plasma is small compared to the distances between particles, so the energy transferred to its surface is negligible. The probe is a ghost moving through a furnace, surrounded by heat, yet never touched by it in any practical sense. Voyager also experiences thermal radiation from the Sun, which diminishes with distance. By the time it reached the outer planets and the heliopause, sunlight is weak, producing minimal heating. The probe's internal heat dominates its thermal environment, rather than external sources. This means that while scientists talk about high temperatures in plasma, the spacecraft itself remains comfortably within operational limits, insulated from any direct threat. Spacecraft orientation helps as well. Voyager's instruments and antennas are carefully angled to minimize energy absorption from the Sun and plasma flux. Radiative panels release excess heat into the vacuum, balancing internal generation and external energy. This passive thermal control is subtle but effective, ensuring that the probe can function for decades without the need for active cooling, which would have been impossible with available power. The materials used for the spacecraft's construction are exceptionally resistant to thermal stress. Aluminum alloys, titanium, and high-grade plastics endure radiation, vacuum, and low-density particle impacts. The hull does not warp or melt because there is no medium to carry enough heat into the material. The few particles striking its surface are insufficient to overcome the thermal inertia of the spacecraft structure. Voyager's continued operation is a testament to careful materials engineering. Even in regions of higher particle density, such as near planetary magnetospheres, the probe is designed to dissipate energy without damage. Heat generated by particle impact spreads across the hull and radiates into space, preventing localized melting. The design anticipates high-energy encounters, ensuring that no single event could compromise the spacecraft. Over decades, the system has proven resilient against both predictable and unexpected energetic phenomena. Voyager's instruments themselves are compact, minimizing surfaces exposed to energy flux. Sensors are often shielded within compartments, which reduces heat absorption. This approach ensures that the very tools measuring plasma, magnetic fields, and cosmic rays remain safe from the energetic environment they observe. In other words, the instruments are both observers and protected entities within the spacecraft, capable of enduring the harsh conditions at the heliopause. The concept of melting is also relative. Spacecraft components are rated for extreme temperatures far exceeding terrestrial expectations. Voyager's electronics can survive heat and cold far beyond what humans would encounter in daily life. Tens of thousands of degrees in a near vacuum, spread across billions of kilometers, do not threaten the probe because it is not immersed in a conductive medium. The heat is present in theory, but cannot accumulate on the spacecraft in practice. Energy dissipation occurs naturally. Even if a plasma particle collides with the probe at high velocity, the transferred kinetic energy is immediately radiated away in infrared light. There is no atmosphere to trap heat, no material to act as a thermal sink. Space itself is a vacuum that absorbs and diffuses energy without effect. Voyager, therefore, remains cold in terms of material heating while moving through plasma hotter than any furnace on Earth. Voyager's power system generates only a modest fraction of the heat detected in the plasma around it. This internal heat is controlled carefully, with radiators and insulation ensuring that electronics remain at functional temperatures. While the plasma may be thousands of degrees Kelvin, the spacecraft's interior never experiences these extreme conditions. In this sense, the probe survives not by avoidance, but by inherent separation from the surrounding environment. Plasma waves measured by Voyager may carry vast amounts of energy, yet most of this energy is in the motion of particles, not in heat transferable to the spacecraft. The particles are so widely spaced that their collisions with the probe are sparse. Over decades, this ensures that Voyager's structure remains stable. Even in regions described as hot, the risk of melting is purely theoretical, highlighting the contrast between temperature as a physical measure of motion and as a practical hazard. Voyager's velocity through space is also a factor. While fast relative to Earth, the spacecraft moves slowly compared to the speed of charged particles in plasma. This reduces kinetic energy transfer during collisions. Unlike a meteor entering Earth's atmosphere, which compresses air to generate heat, Voyager encounters near-empty space where compression is negligible. Energy transfer is minimal, reinforcing why the probe remains intact despite crossing regions of high-temperature plasma. The probe's survival also relies on the absence of chemical reactions. On Earth, materials melt because chemical bonds break under heat, often aided by oxygen or other reactive substances. In space, there is no such medium. Aluminum, titanium, and plastics are inert in the vacuum of the heliopause, meaning that even energy-bearing particles striking the surface cannot trigger chemical melting. Voyager, therefore, encounters no reactive threats at all. Even prolonged exposure to energetic environments does not lead to cumulative heating. Each particle collision is isolated and insufficient to raise bulk temperatures. The thermal environment of the probe remains dominated by its internal heat and radiative balance. Voyager essentially floats in space, untouched by the kinetic energy surrounding it, demonstrating how vast emptiness protects as much as design. The durability of insulation and coatings further protects against any localized heating. Thermal blankets reflect energy and reduce absorption, while multilayer insulation spreads any minor heat evenly. This ensures that even in the rare case of clustered particle collisions, the energy dissipates harmlessly. The design anticipates extremes beyond what the probe actually encounters, highlighting foresight in engineering. Voyager's continued function proves that material limitations are less relevant in space than in an atmosphere. Heat cannot accumulate without a medium, and the few particles that transfer energy to the spacecraft do so in amounts too small to threaten its integrity. This is the paradox of space. High temperatures can exist without danger, because matter is too scarce to conduct it. Even plasma at the heliopause, with measured temperatures far exceeding thousands of degrees, is effectively harmless to the probe. Voyager's hull intercepts only a few particles per second, insufficient to raise surface temperatures meaningfully. Each impact spreads energy across a vast surface area and radiates into the vacuum, ensuring stability. In effect, the spacecraft moves through a high-energy sea without ever feeling the heat. Voyager's age also speaks to the success of its design. Instruments designed in the 1970s continue to function, demonstrating that the spacecraft can survive decades in regions where temperatures, particle energies, and radiation levels were previously unknown. The fact that it has not melted, nor sustained catastrophic damage, is a triumph of foresight, engineering, and understanding of the vacuum environment. The myth of melting arises from human intuition, rooted in terrestrial experience. On Earth, high temperatures mean danger. In space, high particle temperatures are entirely different. Voyager demonstrates that an object can traverse regions of extreme thermal readings without harm because the vacuum separates energy from material. It is the quiet contradiction of interstellar physics, hot, yet untouchable. Voyager's continued data collection reinforces the lesson that space is protective in ways counterintuitive to our senses. The combination of sparse plasma, thermal design, radiative dissipation, and inert materials ensures that the spacecraft survives where fire cannot exist. The instruments measure heat, but the probe itself feels only the controlled warmth of its own energy systems. It is a vessel perfectly adapted to an environment that would otherwise seem hostile. In summary, Voyager did not melt because space itself is largely empty. The probe's materials are inert and resistant, and its thermal design carefully manages internal heat. The kinetic energy of plasma particles is too dispersed to cause damage, and radiation does not translate into flame. The probe's resilience is a combination of physics, foresight, and robust engineering, allowing it to drift through what seems like a furnace without ever being consumed. Its survival is a triumph of both science and imagination. In the vast expanse where Voyager drifts, tiny variations in particle density, magnetic fields, or plasma waves are amplified across unimaginable distances. These small changes, almost imperceptible at first, become profound lessons in understanding the heliopause and interstellar space. Voyager's instruments, sensitive to the slightest deviations, record these subtle differences, revealing that even the smallest motion can have consequences that ripple through the solar system. It is a universe where nuance governs vast processes. A shift of just a few nanoteslas in magnetic field strength can signal a reconnect ion event, where field lines break and reform. Voyager captures these minute variations, transforming them into insights about energy transfer at the solar system's boundary. Scientists interpret these changes carefully, recognizing that even minor fluctuations in the magnetic fabric can lead to localized heating, particle acceleration, and turbulence. Each subtle signal is a key to decoding the behavior of the Sun's outermost influence. Plasma density variations, though tiny, also provide crucial information. In regions where particle density increases slightly, Voyager detects the slowing of solar wind, suggesting that interstellar pressure is pressing back. Conversely, decreases in density indicate relaxation of the heliopause, allowing the Sun's influence to expand temporarily. These delicate measurements highlight the dynamic equilibrium between solar and galactic forces, emphasizing that even small changes shape the large scale. Structure of the boundary. Temperature fluctuations in the plasma add another layer of understanding. Voyager records small rises and dips that, when interpreted collectively, reveal the underlying turbulence of the boundary. Tiny energy exchanges between colliding particles, barely detectable individually, accumulate over time to maintain the high plasma temperatures observed at the heliopause. These measurements demonstrate that small, localized phenomena can scale up to influence the thermal characteristics of an entire cosmic boundary. Cosmic ray intensity also responds to subtle changes at the heliopause. When the magnetic threads shift slightly, or when plasma density alters, the flux of galactic cosmic rays entering the solar system changes accordingly. Voyager's data show that even minor modifications in the magnetic and plasma environment create variations in radiation exposure. These small shifts teach scientists how the Sun's boundary acts as a protective shield, and how delicate that shield is in maintaining planetary safety. Voyager's instruments themselves illustrate the principle of small changes leading to big lessons. Tiny adjustments in the probe's orientation or sensor calibration allow for more precise detection of weak signals. By monitoring even the faintest variations, scientists can reconstruct entire interactions in the boundary, demonstrating that careful measurement of small phenomena can illuminate processes invisible to the naked eye. Precision is the bridge between subtle change and profound insight. The motion of Voyager itself contributes to understanding these small changes. As the spacecraft drifts, it encounters gradual transitions in particle density and magnetic field orientation. Each minor variation is recorded and compared with previous data points, revealing patterns that unfold over months or years. The long timescale of observation allows scientists to recognize trends that would be impossible to see in a short-term snapshot, reinforcing the importance of cumulative, subtle measurements in scientific discovery. Even the bending of magnetic field lines, barely detectable at first, holds lessons. When solar and interstellar fields meet at small angles, they create minor tension that accumulates over vast distances. Voyager senses these bends, interpreting them as signs of reconnect ion or stress release. Such tiny deviations inform our understanding of energy flow across the heliopause, showing that the edge of the solar system is shaped not by abrupt forces alone but by continuous, subtle interactions. Wave patterns in the plasma also provide insight. Voyager's instruments record small oscillations, faint ripples traveling through charged particles, which indicate underlying turbulence or periodic energy exchange. Each oscillation is tiny, yet its presence reveals mechanisms of plasma heating and particle acceleration. By analyzing these minimal shifts, scientists uncover the processes that maintain the heliopause's dynamic stability, showing that the smallest signals can guide the largest conclusions. Even a slight directional change in particle flow can teach profound lessons. Voyager detects when the solar wind curves or slows in response to interstellar pressure. These small shifts illuminate the balance between outward solar influence and inward galactic resistance. By studying them, researchers gain insight into the boundary's elasticity and resilience, learning how the heliopause maintains equilibrium despite constant motion and pressure from two cosmic sources. Voyager's observations of slow, incremental changes in plasma temperature emphasize the importance of patience in discovery. The spacecraft notes subtle rises and falls over months or years, each contributing to the broader picture of particle energy distribution. These small variations demonstrate that thermal dynamics at the heliopause are cumulative, influenced by countless tiny interactions that, together, produce the surprisingly high temperatures observed. Even minor fluctuations in magnetic turbulence have implications for cosmic ray propagation. Voyager shows that small twists and kinks in the field lines can create channels or barriers for energetic particles. These subtle effects influence radiation levels within the heliosphere and help explain variations in cosmic ray detection over time. The lesson is clear: what seems negligible at first glance can have systemic consequences when scaled to the vastness of space. Tiny shifts in interstellar pressure also produce meaningful responses. Voyager detects small compressions or expansions of the solar boundary that correlate with variations in plasma density and magnetic field alignment. These minute changes, occurring over billions of kilometers, demonstrate the heliopause's ability to respond delicately to forces from the galaxy, revealing a system that balances itself through the accumulation of small adjustments. Voyager's readings of minor plasma velocity changes provide insight into the subtle dynamics of the heliopause. Even a slight deceleration in solar wind particles indicates interaction with the interstellar medium. These minuscule shifts, when combined with magnetic data, reveal patterns of energy transfer and stress distribution at the solar system's edge. Each small measurement contributes to understanding the boundary's behavior as a living, responsive interface. Even tiny rotations in the solar wind's magnetic spiral offer lessons. Voyager shows that a few degrees of shift can influence reconnect ion events and particle flow patterns. These small changes, imperceptible without sensitive instruments, help scientists predict where energy will accumulate or where cosmic rays may penetrate. They exemplify the principle that in space, minor adjustments can trigger large-scale phenomena across immense distances. Voyager also demonstrates that small changes in data interpretation can yield big insights. Tiny anomalies in particle flux, once considered noise, were later recognized as indicators of heliopause crossing. This teaches that careful analysis, attention to detail, and patience in examining minute variations can reveal events of immense significance, transforming faint signals into groundbreaking discoveries. Subtle variations in plasma wave frequency carry lessons about boundary turbulence. Voyager records these tiny shifts, showing that energy propagates through the heliopause in gentle pulses rather than violent bursts. This quiet movement teaches scientists about the mechanisms of energy dissipation in space, highlighting the cumulative impact of small oscillations over immense volumes. Even the smallest change in particle trajectory can signal magnetic reconnect ion. Voyager detects these minute deviations, allowing scientists to map the invisible threads of the Sun's magnetic field. The spacecraft demonstrates that small motions can reveal the structure of vast systems, teaching that patience and precision can turn faint clues into comprehensive understanding. Minor shifts in cosmic ray arrival angles are another source of insight. Voyager's data show that even tiny changes in magnetic alignment influence the path of energetic particles, demonstrating how small variations at the boundary have ripple effects throughout the heliosphere. These observations emphasize that large consequences often emerge from subtle causes in the interstellar environment. Slight fluctuations in interstellar plasma density also yield lessons. Voyager measures these small differences to infer local turbulence, energy dissipation, and magnetic field interactions. These tiny variations accumulate to shape the environment that defines the edge of our solar system, showing that even negligible changes can be significant when viewed on cosmic scales. The spacecraft's long-term monitoring reinforces that cumulative small changes matter. Year after year, Voyager's instruments track subtle trends that reveal shifts in the heliosphere's structure and dynamics. Each minor measurement contributes to a narrative of movement, energy exchange, and equilibrium, underscoring the idea that slow, incremental observation is critical for understanding systems on a galactic scale. Even small anomalies in data are instructive. Voyager's instruments pick up variations initially thought to be errors, which later proved to be genuine signals from the dynamic boundary. These tiny discrepancies became valuable lessons in interpreting subtle signals, emphasizing that close attention to minor details can uncover the universe's hidden patterns. Subtle changes in thermal energy recorded by the spacecraft illuminate particle interactions. Voyager captures faint variations in plasma heating, revealing how collisions between sparse particles produce the high temperatures observed. Even though each interaction is minute, their cumulative effect informs our understanding of energy balance at the heliopause. Minor differences in magnetic field orientation between readings help map the heliopause's fine structure. Voyager shows that small angular deviations can indicate regions of reconnect ion or tension, teaching that the fabric of the boundary is intricate and responsive. These observations illustrate how minute measurements can unlock complex phenomena invisible to casual observation. Even tiny, slow waves in the plasma density provide lessons. Voyager detects oscillations so gentle they could be dismissed as noise, yet analysis reveals patterns of pressure exchange between the solar wind and interstellar medium. These subtle movements inform models of heliopause elasticity, demonstrating that small-scale activity accumulates into large-scale behavior. Small adjustments in Voyager's trajectory over decades have helped refine measurements. Tiny variations in angle and orientation allow the spacecraft to sample different regions of plasma and magnetic fields, providing a more complete picture. These minute navigational changes emphasize that precision in both engineering and observation can magnify understanding. Minor but consistent readings of energetic electrons reveal small-scale turbulence. Voyager's instruments detect localized fluctuations that hint at larger processes of particle acceleration and magnetic reconnect ion. These subtle insights demonstrate that even the smallest signals can reveal mechanisms responsible for heating and shaping the heliopause. Small deviations in the timing of plasma waves carry lessons. Voyager measures delays and phase shifts, which correspond to energy propagation through the thin layer of particles. Even tiny differences in timing inform scientists about the dynamics of wave-particle interactions, showing how subtle observation can reveal processes that govern large-scale structure. Subtle changes in interstellar radiation detected by Voyager highlight the influence of the heliopause. Even minor variations in flux indicate shifts in magnetic or plasma conditions. By studying these tiny changes, scientists learn how the Sun's protective bubble modulates energy from the galaxy, emphasizing that small adjustments produce large-scale effects. Even minute fluctuations in Voyager's onboard systems provide insight. Instrument sensitivity, drift, and response to environmental factors teach engineers how to interpret readings accurately. These small internal variations inform methods of calibration, ensuring that faint cosmic signals are not misread or overlooked, highlighting the importance of careful attention to detail. The cumulative lessons from small changes reveal the heliopause as a complex, responsive boundary. Voyager demonstrates that subtle variations in plasma, magnetic fields, particle flow, and cosmic rays provide a mosaic of information. Each minor measurement contributes to a larger understanding, proving that in space, small changes indeed produce big lessons.